How does a red spark become a world? What secrets lie in dust and stone? How does silence make Mars feel alive? For as long as humans have gazed at the night sky, a faint red light has whispered to our imagination. Mars, bright and rust-coloured, drifts among the stars like a quiet ember. In the stillness of midnight, you might find yourself drawn to that subtle glow, wondering what secrets lie on that distant world. There is a gentle pull in the sight of it, a whisper as old as our earliest dreams, inviting us to look up and listen. We once named this wandering star after gods of war. In ancient lore, it was an omen, a celestial fire sparking both fear and curiosity. Yet even then, beyond the fears, there was wonder. The red planet hung in the sky, constant yet mysterious, moving in ways that puzzled early astronomers. As they traced its slow dance across the heavens, they felt an urge to reach out across the darkness. Centuries passed. Telescopes grew stronger, and Mars came into clearer view. On late summer nights of the 19th century, some observers believed they saw straight lines etched on its surface. Canals, they thought, built by Martian hands. It was an illusion, but one that ignited imaginations. Stories blossomed of wise Martian civilizations and golden deserts under alien suns. Around campfires and in drawing rooms, people spoke in hushed tones of the red world and what might live there. The dream of Mars took root in our culture like a timeless folk tale, passed from generation to generation. Long before rockets roared into the sky, writers sent their minds to Mars. Through pages of speculative fiction, we journeyed there in thought. We met green-skinned beings by imagined oases, or travelled with intrepid explorers across rusty plains and polar ice. Each story, each wild theory, was a quiet promise that Mars was not just a point of light, but a place we might one day touch. The yearning to step onto Martian soil, to leave footprints in red dust, began to feel like a destiny woven into our future. Now, in our modern age, the dream is no longer only the stuff of bedtime stories. We have built machines and sent them across the void to Mars. We have watched in wonder as a parachute opened in thin Martian air and delivered a rover safely to the ground. Through robotic eyes, we have witnessed the sun setting on a Martian horizon, painting the sky in hues of blue and gold. With each new photograph of its quiet craters and windswept dunes, Mars speaks to us a little louder. It beckons not as a distant fantasy, but as a real place, one that in the not-too-distant future might welcome us. Imagine standing on that foreign ground. The sky above is tinted butterscotch by a fine dust hanging in the thin air. Beneath a pale sun, the land stretches out in quiet shades of red and brown. Not far away, a dust devil twists silently across the plain, stirring up coppery sands. Twilight comes, and with it one of Mars's two small moons, Phobos, rising like a swift phantom in the dusky sky. In the silence, you hear only your own breath inside your helmet, a gentle reminder that you are a stranger in this place. The air is cold and still, and the horizon seems endless. In that moment, you feel the weight of all those centuries of wonder. The same red world that was once only a spark in the sky is now solid ground beneath your boots. The whispers that called to ancient sky watchers have guided you here, and as you gaze at the strange and beautiful landscape, you carry in your heart the hopes and curiosity of countless dreamers who dared to imagine this place long before it was truly possible to come. This journey begins with a whisper and a promise. As we set our sights on Mars, we carry with us the hopes of those who looked up through smoky campfire haze and early telescopes, who dared to dream of the red world up close. It is a patient, quiet hope, growing brighter year by year. Mars awaits, silent, ancient, and full of mystery. And the first steps toward it are guided by the soft echoes of all those dreams that came before. If we drift closer now, leaving the black of space for Mars's thin atmosphere, a new world reveals itself below. From high above, Mars is a canvas of reddish-brown, ochre, and gold. Dark patches and bright dusty plains blend together like the strokes of an ancient painting. Near the poles, you can see caps of white ice and frozen gas catching the sunlight. Across the broad middle of the planet, the rust-coloured expanse is marked by ancient scars and colossal features that have no equal on our home world. This is Mars's face, both familiar in some ways and hauntingly alien in others. Spread across this dry world are volcanoes that once spat fire into the sky. One volcano, Olympus Mons, towers higher than any mountain on Earth or anywhere in the solar system. Its base would cover an entire region, and its peak reaches so high that it nearly touches the edge of Mars's atmosphere. If you stood on its gentle slopes, the summit would be so far above you that you might not even realize you were on a mountain at all. And then there is the Great Canyon, Valles Marineris, a chasm running along the planet's belly for thousands of miles. It's so long that it would stretch from one side of a continent to the other, and so deep in places that even the tallest peaks of Earth would be lost within it. Standing at its edge in your mind's eye, you would see cliffs that drop away into darkness, a vast emptiness below. Elsewhere, countless craters pockmark the terrain, their rims softened by time. Some craters hold rippling dunes shaped by the wind. Others cradle patches of frost that gleam in the feeble morning sun. Every valley, mound, and plain tells a story of a planet that has seen volcanoes rage and waters flow, ice accumulate and retreat. Meteorites crash and winds endlessly reshape the dust. The air on Mars is almost not air at all by earthly standards. Thin, cold, and unyielding. It is a fragile veil of mostly carbon dioxide, with only a wisp of other gases. During the day, under a distant sun, the ground may warm a little, but the heat quickly slips away into the thin atmosphere. By night, without a thick blanket of air to hold on to the warmth, the temperatures plummet under clear skies filled with stars. Mars is a world of harsh extremes. At noon, near the equator, the sun might feel weak but comforting on your suit, and the ground underfoot could be as mild as an autumn day back home. But just a few hours later, after sunset, that same spot would become brutally cold, cold enough to freeze any exposed water in an instant. In this spare atmosphere, there is no breeze you can feel on your skin without a pressure suit, but the wind is there, only barely perceptible through your visor as it moves the dust in ghostly puffs. Look up during the day, and you might be surprised by the colour of the Martian sky. A butterscotch hue, a pale orange-yellow halo encircling the sun. Fine grains of dust hang suspended in the air, colouring the sky and softening the sunlight. When evening comes, the sky performs a gentle trick. As the sun sinks, The dusty air turns the light blue around the fading sun, a cool twilight glow in contrast to the warm daytime sky. Sometimes, thin icy clouds form high above, drifting and shimmering as they catch the last light. Around the towering volcanoes, afternoon air can rise up the slopes and condense into wispy clouds that ring the peaks. And in the polar winter, as temperatures plunge, carbon dioxide from the air freezes into tiny crystals, making faint fogs and clouds that hover near the frigid ground. Though the atmosphere is thin, it still can surprise you with delicate displays of light and shadow. Mars knows weather, but not the kind we know on Earth. There are no gentle rains, no thunderclouds rolling on summer afternoons. Instead, the weather here is written in wind and dust. On a calm day, you might see dust devils, tall, twisting whirlwinds, dancing silently across the open plain. They leave dark tracks on the surface that only orbiters notice, proof of their fleeting presence. When the winds grow stronger, they carry grains of rusty sand high into the sky. A simple breeze can swell into a dust storm, and dust storms can grow until they ride the high atmosphere and encircle the entire planet. Every so often, Mars succumbs to these global dust storms that shroud the surface in a hazy red gloom for weeks, letting only a dim bronze light reach the ground at noon. Eventually, the storms subside. The dust drifts back onto the surface like a blanket gently laid down, changing the patterns on the ground until the next wind rearranges them again. The poles of Mars hold their own mysteries. In winter, under months of darkness, the polar regions become seas of frozen carbon dioxide. The atmosphere itself falls as frost, coating the polar plains in a layer of dry ice that stretches for hundreds of miles. These caps of white gleam under the weak sunlight when it finally returns. As spring comes, the sunlight awakens the polar landscape. The frozen carbon dioxide sublimates, turns directly from ice to gas, and wafts back into the atmosphere. You could almost imagine the planet breathing in and out with the seasons, the caps shrinking in summer, growing again in winter. Underneath this seasonal frosting lies permanent ice, ancient layers of water ice that remain year-round, holding the history of Mars's climate in their frozen stripes. Occasionally, as the seasonal ice thaws, jets of gas erupt through the thawing crust, spraying dark fans of dust over the ice and giving the polar terrain a strangely active, almost alive appearance, even in the silence. This is a silent world, a place where only the whisper of the wind and the soft fall of dust break the quiet. There are no sounds of running water, no rustling forests, only a deep stillness, broken by the faint sighing of a thin breeze. The landscape around you is painted in reds and browns under a pale peach sky, waiting in quiet for something that has not yet come. Yet, despite the stillness, Mars is not static. The days here, just a little longer than Earth's, still dawn and dusk with gentle regularity. The seasons still turn, slower, perhaps, and more subtle, but they turn all the same. As night falls in this imagined moment, you watch the stars appear one by one over a strange horizon and see a small moon hurry across the sky. Mars rotates and revolves, marking the passage of time in its own way, under the gaze of a sun that shines only half as warmly as we know. Standing there, one begins to sense how time on Mars would be its own experience, a different cadence of days and years amid the endless, patient quiet of this alien world. A day on Mars, often called a sol, is a strangely familiar stretch of time. Roughly 24 hours and 39 minutes long, a Sol follows a rhythm just a little slower than an Earth day. The sun takes its time crossing the Martian sky, lingering slightly longer before it dips below the horizon. For an explorer on Mars, that extra 39 minutes might pass almost unnoticed at first, like a gentle extension of daylight, or a few more moments of stars before dawn. Over time, though, those minutes add up. The mornings creep later, the sunsets drift into new hours. Mars quietly teaches you a different cadence of day and night, one that would eventually feel natural as you settle into life on this distant world. To those watching from Earth, working with robots on Mars, that slow rhythm can pose a challenge. Scientists and engineers have sometimes shifted their own schedules to Mars time when guiding rovers across the red sands. They wake and sleep according to the Martian clock, letting the rising and setting of the sun in Gale Crater or Jezero guide their day. It's a disorienting routine on Earth. Imagine eating breakfast at midnight and seeing dawn at noon. Yet it offers a glimpse of what future pioneers might experience. On Mars itself, one would gradually grow accustomed to this new normal. The human body, ever adaptable, would adjust to 24 and a bit hours, syncing with the steady cycle of Martian light and dark. In the end, a day on Mars would still be a day, sunrise, noon, and sunset, just gently stretched. But time on Mars unfolds on a grander scale as well. A Martian year lasts nearly 687 Earth days, almost 2 Earth years. With this long year come seasons that linger. Mars, like Earth, is tilted on its axis about 25 degrees, giving it spring, summer, autumn, and winter. But because Mars takes its time around the sun, each season lasts nearly twice as long as what we know. Imagine a winter night that stretches on and on, the sun absent for months near the pole, or a summer daylight that seems to never end. In the thin air, the differences between seasons are subtle compared to Earth's dramatic changes. Still, they exist. The polar ice grows and recedes, the colour of the atmosphere shifts with the amount of dust, and the temperatures inch up and down as the planet makes its slow loop around the sun. Martian seasons have their own character. The orbit of Mars is more elliptical than Earth's, meaning at certain times the planet is significantly closer or farther from the sun. When southern summer comes, Mars is at its closest, and the sunlight grows a little stronger. The southern deserts warm, and often this is when Mars's most ferocious storms arise. A small dust devil might spin into a larger dust storm, and that storm might grow until it sweeps across half a world. It's as if Mars, in its summer excitement, sometimes wraps itself in a dusty shawl. In contrast, when Mars is farther from the sun, the winters are especially cold and still. In those times, the air freezes onto the poles, and even the dust seems to settle, as if the planet holds its breath in the deep cold of aphelion. Each year, this cycle of storm and stillness, warmth and cold, plays out in a slow rhythm. To a human observer living on Mars, the changes might come gradually. Perhaps the sky takes on a tannish haze, signalling dust on the rise, or the mornings grow a bit cooler and the daylight a bit shorter as winter slowly approaches. For anyone making a home on Mars, keeping time would mean embracing these differences. One might hang a Martian calendar on the habitat wall, with unfamiliar constellations of dates marking the passage of about 669 sols in a year. Birthdays would come less frequently if counted in Martian years, each one nearly twice the celebration by Earth's calendar. The concept of a week or a month might be reinvented to fit the new sky. perhaps tied to the phases of Mars's little moons or the milestones of the seasons. Imagine stepping outside your habitat to watch the beginning of spring, the sun climbing a bit higher each sol, melting away patches of winter frost. Or watching the first dusting of carbon dioxide snow settle in autumn, the herald of a long winter's night. Time on Mars would be something you feel in the changing air and the colour of the sky. It would require patience, living more slowly in some ways, as the planet turns and orbits at its own pace. And yet, while Mars has its own clock and calendar, it remains tethered to the dance it shares with Earth around the Sun. For those of us on Earth planning a journey to the red planet, timing is everything. The two worlds draw near to each other only at rare intervals. Roughly every 26 months, Earth and Mars line up just so, bringing the planets closer together and making the voyage a bit easier. These are the launch windows, brief periods when a spacecraft can set off on the most efficient path, riding a wave of orbital mechanics toward Mars. Miss that window, and one may have to wait over 2 years for the next opportunity, as Mars wanders far out of reach. Even when launched at the perfect time, a ship must still spend long months coasting through space to catch up with Mars. In this way, the rhythm of Mars's orbit dictates the rhythm of our journeys. Patience and planning become as important as rocket fuel. Mars teaches us that we must move in harmony with the solar system's grand clock, setting forth only when the timing is right. Mars is far away, so far that even our thoughts stretch when imagining the distance. Picture the solar system as a vast racetrack, with Earth running on an inner lane and Mars on an outer one. Earth moves quicker, making a lap in 1 year, while Mars plods along, taking almost 2 years for its circuit. Every now and then, Earth comes up from behind and overtakes Mars. In those moments, the two planets are closest together, like two runners briefly side by side. At the nearest approach, Mars might be about 55 million kilometers away, still a daunting distance, but relatively close in cosmic terms. At the farthest, when Mars is on the opposite side of the Sun, that distance can stretch to over 400 million kilometers. The red planet becomes a faint ember in the sky, so distant that even light takes more than 20 minutes to bridge the gap. The dance of these orbits means the distance between our worlds is always changing. A slow rhythm of approach and retreat that influences when and how we reach across space. To travel from Earth to Mars, one cannot simply point a rocket and fire straight at the red world. Instead, the journey follows a carefully timed, curved path through the void. When a launch window opens, a spacecraft departs Earth at just the right moment and angle, aiming not for where Mars is today, but where Mars will be months in the future. It's like throwing a message in a bottle into a moving river, trusting it will meet a friend downstream. The trajectory arcs away from Earth, catching the Sun's pull to bend its course, and eventually intersects Mars's orbit. For roughly 6 to 9 months, the spacecraft coasts in deep space, covering tens of millions of kilometers. Inside, any voyagers would watch as the blue dot of Earth shrinks behind them, while the red dot of Mars grows slowly ahead. It is a long and quiet voyage. Each passing day, the sun appears a little smaller, and the glow of home a little fainter. The crew lives in a small, self-contained world, carrying with them a bubble of Earth's warmth through an ocean of emptiness. During this long transit between worlds, time and distance are constant companions. The crew, if there are people on board, might find ways to mark the passing weeks, perhaps noting each million kilometers traveled, or celebrating the halfway point when Earth and Mars are equally distant. Looking out a porthole, there is mostly darkness. The stars shine cold and steady, and the sun, though still brilliant, has lost some of the fierce glare it had near Earth. There is no up or down in the weightlessness of the ship. Day and night become concepts measured by routines rather than sunrise or sunset. The travelers float through their days, working through checklists, exercising to keep their bodies strong, finding small ways to break the monotony. In such silence, even a simple routine becomes precious. They might gather at a window each evening to watch Earth, now just a tiny glint, and to search for Mars ahead, that faint reddish beacon growing a little brighter week by week. It's a tranquil, solitary journey, an odyssey through a vast ocean of stars. Back on Earth, those who said goodbye can only watch Mars in the night sky and wait. Communication becomes an exercise in patience. Early in the voyage, when Earth and Mars are not so far apart, a message from the spacecraft might take only a few minutes to arrive. It's almost like a quick exchange across a great distance. But as the gap widens, so does the delay. Soon a radio signal, traveling at light speed, takes 10 minutes or more to cross the void. By the time the ship nears Mars, a call home could take 20 minutes or longer one way. Imagine saying hello and having to wait nearly an hour to hear a response to your greeting. There's no real-time conversation, no instant reassurance from a familiar voice across space. Instead, each message is like a note in a bottle cast into a slow current, carrying hopes and updates that eventually wash ashore on the other planet. In this way, every communication reminds both sender and receiver just how far apart they truly are. The distance affects more than talk. It tugs at the heart. Standing on Mars, if you were to look up at the sky on a clear night, you would see Earth as a bright star, pale blue, with a tiny companion dot of the moon nearby. All of human history, every sea and mountain, all your friends and family, are on that tiny speck of light shimmering above the horizon. In that moment, the realization of being truly away sinks in. Help from Earth is not immediate. It cannot be. If something goes wrong, those on Mars must solve it largely on their own, guided only by advice sent many minutes or hours earlier. This remoteness is both humbling and profound. It means a Martian settler lives in a world almost entirely self-reliant, with Earth's bustle and comfort a distant memory carried in the heart and in the slow stream of messages from home. Each person on Mars carries the warmth of Earth within them, finding strength in the knowledge that their distant home is up there in the sky, watching over them from millions of kilometers away. There are even times when Mars slips entirely behind the Sun from Earth's point of view. During these weeks of solar conjunction, the great star in the middle blocks our signals. Radio waves from Mars can't pierce the Sun's hot, ionized corona, so for a short period, Mars all but falls silent to Earth. Mission controllers plan for this, instructing their rovers and landers to sit tight or work autonomously when communication is cut off. One day, human pioneers will experience this quiet spell too. They'll know that for a few days or weeks, no new messages will arrive from Earth. They might watch the sun dip on the Martian horizon and think of Earth hidden beyond it, unreachable until the planets move along in their paths. In that enforced silence, they will rely completely on their own community and resources, reminded anew of the vast distance that separates them from home. These vast distances and delays make clear that Mars is not just another destination. It is truly another world. Getting there and staying there will stretch our technology, our minds, and our resolve. We must learn to navigate not only space but time, aligning our launches with celestial clocks, enduring long months confined in a spacecraft, and accepting the built-in loneliness of each exchange across the void. The gulf between Earth and Mars demands patience and resilience, unlike any journey humanity has undertaken before. And yet, knowing this, we prepare ourselves. Beyond the challenge of distance itself, we face the harsh environment that awaits travelers and settlers. In the silent vacuum between planets, radiation from the sun and distant stars permeates every spacecraft. On Mars's surface, gravity is weaker, a constant test for bodies built on Earth. And everywhere on Mars clings a fine dust, ancient, powdery, and pervasive, that works its way into machinery and homes. These are the hazards that lurk in the silence, the trials we must overcome to build a new home on the red planet. Forewarned, we approach them with respect and ingenuity. The journey to Mars is not easy, but as our dream compels us forward, we remain determined to greet these challenges with hope and perseverance. Mars may greet us with breathtaking scenery and quiet sunsets, but its beauty comes with dangers hidden in the silence. On the journey there, and on the surface itself, challenges lurk that our species has never before faced firsthand. It's not the threats we can see or hear that pose the greatest risk. There are no towering beasts or alien storms of legend, but rather the subtle, invisible, and pervasive hazards that will test the limits of our bodies and ingenuity. As we set out to build a city on Mars, we must reckon with these threats. The unseen rain of radiation that falls on a world with little natural protection, the unfamiliar pull of a weaker gravity, and the omnipresent dust that coats Mars like a fine powder. Each of these elements of the Martian environment can harm or hinder us if we're not prepared. Understanding them is the first step to living alongside them. In space and on Mars, radiation is a constant, invisible drizzle of high-energy particles. Back on Earth, we are sheltered by our planet's thick atmosphere and magnetic field, which together form a protective cocoon. On the voyage to Mars, however, a spacecraft leaves that cocoon behind. Every day of the journey, cosmic rays from distant stars and bursts of charged particles from the sun pass through the ship. You cannot see or feel them, but they slice through in silence, bit by bit, affecting the cells of the body and the electronics of the vessel. On Mars's surface, the situation is only a little better. Mars has no global magnetic field, and its atmosphere is far too thin to stop much of the space radiation. Standing on Mars, you would receive many times the radiation dose you'd get on Earth. Exposure that, over months and years, could raise the risk of cancer or other illnesses. For people living in a Martian city, shielding from this invisible threat will be vital. Habitats might be buried under layers of Martian soil, or built into hillsides, or even caves, using the planet's own rocks and dirt as a protective blanket. Water tanks could be stationed along the walls of living spaces, since water is excellent at soaking up radiation. And during the rare but dangerous solar flare events, when the sun unleashes a sudden storm of energetic particles toward Mars, colonists might retreat into special storm shelters, perhaps a module lined with extra shielding or an underground vault, until the storm passes. It's a strange thought that on the clearest, brightest Martian day, beneath a pale sky, an unseen storm of radiation could be falling. But knowing it's there means we can plan and protect ourselves, turning Mars from a lethal environment into a livable one. Then there is the challenge of gravity, or rather, the lack and reduction of it. We usually don't give gravity a thought on Earth. It's the ever-present force that keeps us rooted and shapes our body's strength. During the journey to Mars, though, travelers will spend long months in weightlessness. Freed from gravity's pull, the human body begins to change in subtle, disconcerting ways. Muscles that no longer need to fight against weight start to weaken from disuse. bones, relieved of their burden, begin to lose calcium and density. Astronauts aboard the space station exercise vigorously every day to counteract these effects, running on treadmills with harnesses to hold them down, or straining against resistance machines to keep muscles engaged. A crew bound for Mars would have to do the same, treating exercise not just as routine, but as essential medicine. Some designs even imagine spinning parts of the spacecraft to create a bit of artificial gravity by centrifugal force, letting the crew occasionally walk or sleep with a sense of weight. Even once they land, the challenge continues in a new form. Mars offers gravity, but only about 38% of Earth's. In this lighter pull, a person can lift heavy objects more easily and might even feel a spring in their step, able to jump higher than they ever could back home. At first, that difference might be a welcome novelty. Imagine bounding along in a bulky suit, covering ground with moon-like leaps. But over months and years, living with just 1/3 of Earth's gravity could pose problems we have yet to fully understand. Will the human body adjust and find a new equilibrium, or will it continue to weaken because even Mars's gravity is not enough to maintain Earth-hardened bones and muscles? Colonists might need to wear weighted vests during daily tasks to simulate a bit more heft, or keep up rigorous workout regimens to stave off atrophy. Medical teams will carefully monitor how hearts pump and how bones rebuild, or don't, in this low-gravity world. And if one day a settler who has lived many years on Mars tries to return to Earth, they may find the old gravity almost unbearable until their body readapts, if it can. Thus, part of the architecture of a Mars city will likely include well-equipped gyms and perhaps even spinning habitats or special gravity chambers in the future. It's a paradox that in order to thrive on a world with less gravity, we must simulate the heavy load of Earth just to keep our bodies strong. And everywhere on Mars, there is dust. Not the ordinary house dust we occasionally wipe off a shelf, but a pervasive, ultra-fine powder that covers everything and spares nothing. This dust is the product of eons of rock grinding against rock, a talcum-like powder of iron oxide and minerals that gives Mars its red hue. It's so fine that it creeps into the smallest crevices. It clings electrostatically to suits and rover wheels, riding indoors on boots and equipment. Martian dust is not only fine, but can be chemically reactive. It contains compounds called perchlorates, which on Earth are used in rocket fuel and can be toxic to humans in high concentrations. This means that astronauts will have to be careful not to bring too much dust inside, where it could contaminate air or water supplies. Spacesuits might need to have brush-off stations or airlocks that can blow off particles before the wearer enters living quarters. Over time, the dust is an abrasive enemy of machinery. Gears can grind down, seals can wear out, and solar panels can become coated and lose efficiency. We remember that even on the Moon, astronauts found dust to be a stubborn, clinging nuisance that scratched their visors and wore on their lungs. On Mars, it will be an everyday challenge. During Mars's infamous dust storms, when winds lift particles into a global haze, the sun can weaken to a mere dim glow. A colony relying on solar power would need backup systems, batteries or reactors, to endure such long dusty darkness. Vehicles and instruments left outside must be designed to resist being choked by dust buildup. Living with Martian dust will require constant diligence. The city's architecture might include smooth, rounded surfaces that shed dust easily, electrostatic covers that can be activated to shake off dust, or even fleets of little cleaning robots that roam around wiping lenses and panels. Perhaps daily chores for the crew will involve vacuuming out air filters and inspecting seals, or routinely swapping out dust-clogged components for clean ones. It's a never-ending battle against an enemy that's everywhere and nowhere, just a fine red film settling quietly over all that we build. But bit by bit, through good design and careful habits, this too can be managed. Radiation, low gravity, relentless dust. These are formidable adversaries that Mars sets before us. They remind us that we are far from the gentle haven of Earth, in a place not naturally meant for human life. And yet, none of these hazards are insurmountable. With knowledge, creativity, and determination, we can shield ourselves from radiation's invisible touch, keep our bodies strong in the light pull of Mars, and even tame the dust so we can live alongside it. In confronting these challenges, we push the boundaries of science and engineering. We become more resilient as a species. It's worth asking, why do this at all, given the risks? What drives us to overcome such daunting obstacles to settle a distant world? The answer lies in what Mars offers us in return: the promise of discovery, the hope of securing our future, and the allure of a grand human adventure. Why Mars, and why now? To answer that, we must explore the purposes that compel us, the science we can do, the security we can gain, and the story we can create by making Mars part of our world. Mars holds answers to questions that have tugged at human curiosity for generations. One of the most profound is, did life ever exist beyond Earth? Mars, with its dry riverbeds and ancient lakebeds, whispers of a time long ago when water flowed across its surface. If tiny microbes ever swam in those Martian streams, or dwelled in the mud of a vanished lake, they might have left traces behind. Fossil imprints in rock or telltale patterns in the soil, waiting to be discovered. By going to Mars, scientists hope to read this ancient record. A discovery of past life, or even present microbial life hiding in a warm pocket underground, would forever change our understanding of our place in the universe. Even if Mars turns out to be sterile, that knowledge is valuable too, for it will teach us why two neighboring planets, Earth and Mars, ended up so differently, one teeming with life and the other seemingly barren. Beyond the life question, Mars is a historian of the solar system. Its rocks and landscapes are relatively unchanged since their formation, offering clues to how planets form and evolve. Mars once had volcanoes that would dwarf any on Earth and floods that carved out canyons. Exploring these features can tell us about processes that shaped all rocky planets. Drilling into Martian soil, examining its chemistry and mineral layers, could reveal how Mars lost most of its air and water over time, and by extension, how Earth has kept its own. Each sample a human geologist picks up on Mars, every measurement taken on the red plains, fills in another chapter of the story of our planetary neighborhood. In exploring Mars, we're not just learning about Mars, we're learning about Earth and the entire history of our solar system, gaining perspective on how unique or common our own world might be. There is another, more pragmatic reason to go, a reason rooted in survival and foresight. As nurturing as Earth is, history reminds us that life here can be vulnerable to sudden catastrophe. The dinosaurs, for all their dominance, could not escape extinction when their world was upended. But humanity has knowledge and tools the dinosaurs never did. By establishing a presence on Mars, we create a second home for our species, a place where humans could carry on even if some disaster struck Earth. It's a distant insurance policy for humanity, a way of not putting all our eggs in one basket. Mars, for all its harshness, offers the raw materials for a foothold. There is water locked away in ice, and perhaps in briny underground reservoirs. Water to drink, to split into oxygen to breathe, and hydrogen for fuel. There are abundant minerals in the soil that could one day be turned into building materials, metals, or nutrients for crops. The sunlight, while weaker than on Earth, can still be harnessed for energy, and the thin air, mostly carbon dioxide, can become a feedstock for making oxygen and even plastics or fuels with the right techniques. Learning to live on Mars would teach us invaluable lessons about closed-loop life support and self-sufficiency, skills that could help us live more sustainably on Earth as well. The technologies needed to grow food in a dome on Mars or recycle water in a habitat might yield breakthroughs that make farms more efficient or water purification better back home. In reaching for Mars to safeguard our future, we also hold up a mirror to Earth, learning how to protect and cherish our first home by mastering living on a new one. Then there is the matter of aspiration, the story we tell about ourselves as explorers. Going to Mars is not just a scientific endeavor or a backup plan. It's a chapter in the human epic. The red planet has beckoned to us in our imaginations for so long that attempting to live there is a deeply symbolic move. It represents pushing the frontier, as humans have always done. There's a line connecting the first humans who wandered out of Africa to people settling new continents, to astronauts stepping onto the moon, and that line now extends to Mars. It is the next horizon. Mars is the new frontier of our time, tantalizing and challenging in equal measure. The very difficulty of reaching and surviving there is part of the allure. It calls on our courage and ingenuity, daring us to do something monumental. The pursuit of this goal can inspire and unite. Children in schoolrooms today might pin up pictures of Mars rovers and rockets, dreaming of becoming the first to walk on the red sands. Nations that often compete might find common ground in the grand enterprise of exploration, much as international crews now collaborate on the space station above Earth. The story of building a city on Mars is a hopeful narrative for humanity. It says that despite our troubles and differences, we are capable of remarkable things. We can set aside short-term concerns to work on something that won't be fully realized for decades, even generations, a gesture of faith in the future. When humans finally stand on Mars, and later when families live there, it will be a testament to our creativity, cooperation, and perseverance. The very act of doing it will write a new story for our species, one of adventure, adaptability, and hope that will echo through time. It reminds us that we are explorers at heart, never content to stay put, always wondering what lies beyond the next hill or the next planet, and willing to journey there to find out. Why now? Simply put, we stand at a moment in history where this once distant dream is becoming attainable. In the past few decades, our robotic pioneers have transformed Mars from a blurry reddish disk into a mapped world. Orbiters have charted its mountains, valleys, and polar caps in detail. Rovers have trundled across its plains and delved into its rocks, discovering signs of ancient river deltas and organic molecules, teasing our scientific hunger. They have prepared the way, turning Mars from a distant point of light into a real place in our minds, with known landmarks and weather patterns. At the same time, back on Earth, our technology has been catching up with our ambitions. Rockets more powerful and efficient than ever before are being tested, capable of carrying the heavy loads needed for a Mars journey. We've developed precision landing techniques to safely drop payloads on alien terrain and learned how to operate life support systems in the closed environment of space stations. New spacesuits, habitat designs, and tools for extracting water or oxygen from local resources are being prototyped. Multiple nations and private companies are now engaged in a new space age, pooling ideas and racing forward in parallel. The sense that we can do this has never been stronger. Challenges remain, certainly, but they are being whittled down year by year. It feels as though all the pieces, knowledge, technology, willpower, are assembling like parts of a grand puzzle. Now is the time when the question shifts from, can we go to Mars, to, when and how will we do it? For a generation that grew up with rovers on Mars and images of its sunset sky, the idea of living there is no longer fantasy, but an actionable goal. In short, we are ready in a way humanity has never been ready before. With these motivations in mind, the scientific quest, the survival strategy, and the call to adventure, humanity's path to Mars gains clarity and purpose. We understand why we want to go, and we sense that now is the opportune moment to begin. The vision of a city on Mars, once just a science fiction dream, has solidified into something tangible that engineers can draft and planners can schedule. The next step is to turn that vision into reality, piece by piece. And like any momentous endeavor, it starts with choosing the right place to begin. The question now becomes, where on that wide, dusty planet should we build our first foothold? On a world full of ancient craters and broad plains, icy poles and towering volcanoes, where will the first settlers touch down and call home? It's time to survey the red planet with new eyes, not just as explorers seeking knowledge, but as pioneers seeking a land to settle. We have the will to go. Now we must decide where to settle on the vast canvas of Mars. Choosing a home for the first Martian city is no simple task. It's a bit like being the first voyagers arriving at a new continent, but with far less margin for error. In our mind's eye, let us fly above the red planet's surface, scanning the terrain for a place to call home. What do we see? Endless deserts of dust, crater-scarred highlands, titanic volcanoes, shimmering polar ice caps, and canyons that cut through the crust like scars. Among all these dramatic features, we need to find a spot gentle enough to welcome a fragile human beachhead, somewhere with the resources and conditions to give life a foothold on a lifeless world. Down there, somewhere, is a patch of ground that will become the foundation of a new human outpost. Our task is to find it. Several key criteria guide our search. Water is foremost among them. Without water, any settlement is doomed. We'll want to land where ice lies hidden just below the surface, or where frost can be collected, so we have a supply to drink, to grow food, and to make oxygen and fuel. Sunlight is another consideration. Closer to Mars's equator, the sun climbs higher each day, and the climate is relatively milder, offering more energy for solar panels and shorter, less severe winters. But many equatorial areas are dry, with little accessible ice. We might need to balance the need for warmth and solar power against the need for water found in colder, more frozen ground. The terrain itself must be friendly. Flat, stable ground is ideal for landing rockets and building structures. A slope or a jumble of boulders could spell disaster during touchdown or construction. A lower elevation site can be helpful too, because the deeper you go into Mars's subtle atmosphere, the thicker that air becomes, just enough to give a bit more cushion for landing and a slight uptick in air pressure for the colony. Even a small increase in atmospheric pressure can aid in shielding radiation and can make entry descent a tad easier. We also consider the local climate. Some regions are notorious for frequent dust storms or extreme cold snaps, while others might have a more forgiving pattern of weather. The ideal spot would be one with relatively calm weather, moderate temperatures by Martian standards, and as few surprises as possible. In essence, we're searching for a Goldilocks zone on a planet that is by and large hostile. somewhere not too cold, not too dry, with enough sunlight and a cache of ice, somewhere safe to land and live. One promising kind of location lies in Mars's vast mid-latitude plains, those broad, relatively smooth expanses between the icy poles and the equatorial deserts. Picture a gently rolling plain under a peach-tinted sky. The ground is dusty and flat, dotted occasionally with low hills or the eroded rims of old craters. Nothing spectacular at first glance, but just beneath your feet, hidden in the soil, is treasure. Water ice, and lots of it. In fact, orbital instruments suggest that in some of these regions, a shovel pushed into the ground would hit frozen water within a few feet. An outpost here could mine ice simply by baking scoopfuls of dirt. One such region is Arcadia Planitia in Mars's northern hemisphere. It's a place often mentioned by planners because it checks many boxes. Arcadia is broad and relatively flat, making landings less hazardous. It's low-lying, so the air above is marginally thicker than in the highlands. And crucially, data indicates a wealth of ice beneath its surface, likely left from an ancient snowfall or ice age. If you were standing in Arcadia Planitia, you'd see a mostly uninterrupted horizon, just the gentle curvature of Mars, and perhaps the outline of distant crater walls, if any are near. It might seem a little desolate, but that flat emptiness is an advantage. There are fewer rocks to block your path or crack your rover's wheel, fewer steep slopes to complicate construction. The simplicity of the landscape would be inviting to the first pilots trying to land heavy cargo ships on alien soil. In summer, the temperature at midday might rise enough to soften the ground slightly, and in winter it would drop so low that the carbon dioxide in the air could frost out on the surface each night. But day by day, a base here could harvest ice, generating precious water and, through electrolysis, oxygen to breathe and hydrogen for fuel. The northern location would mean colder winters and longer nights than at the equator, but with planning and power storage, those could be overcome. Arcadia Planitia, and regions like it, offer a kind of blank canvas. Perhaps not the most scenic part of Mars, but a stable, resource-rich place to begin writing the story of a Martian city. Another intriguing possibility is to seek natural shelters that Mars itself provides. We turn our attention to the planet's colossal volcanoes and the lava flows around them. Long ago, when these volcanoes were active, rivers of lava burrowed under the surface, hollowing out immense caves known as lava tubes. On Earth, lava tubes can form long, tunnel-like caves when the surface of a lava flow cools and solidifies, while the hot lava beneath drains away. On Mars, where gravity is lower and volcanoes were much larger, some lava tubes could be truly cavernous, large enough to fit cathedrals or city blocks inside. From orbit, we've spotted hints of these subterranean spaces. Deep pits with overhanging edges that look like skylight openings into caverns below. Imagine a colony that finds one of these pits and decides to venture inside. Rappelling down or building an access ramp, the explorers would enter a world unlike any on Mars's surface, dark, still, and insulated. Overhead, instead of thin air and cosmic rays, there's a thick roof of rock, potentially dozens of meters thick. Such a roof would be an excellent shield against radiation and micrometeorites. Inside the lava tube, the temperature might remain more stable, not swinging wildly from day to night. There would be no dust storms in here, no abrasive winds at all, only the dust that you carry in with you. A colony could seal off a section of the tube and pressurize it, creating one of the largest indoor spaces imaginable on Mars, big enough to stroll around in without a suit. You could build entire habitats in there, protected by the natural cave. Locations for these tubes include the areas around the giant volcanoes like Arsia Mons or Pavonis Mons, or in the long lava plains of Tharsis. However, reaching and building in these spots brings challenges. The terrain is rough and sloping, being on the side of a volcano or amid older, rocky flows. The elevation is often high, meaning less atmosphere above to help with landings or to provide even a hint of extra pressure. But the allure of a ready-made refuge is strong. We can picture it: an entrance on a mountainside leading to a hidden city beneath Mars's surface, lights glowing from cave walls, underground farms and living quarters shielded by nature. Utilizing a lava tube would be like settling into a house Mars built for us, adapting its ancient geology into a modern sanctuary. There are other contenders, each with their own appeal and drawbacks. Some have suggested planting the first colony near Mars's polar regions. At first glance, the poles are attractive. Ice is everywhere, not just buried below ground, but right on the surface, as bright caps of frozen water and carbon dioxide. In the height of summer, the polar sun barely dips below the horizon, giving nearly continuous daylight for solar power. One could imagine a base at the edge of the northern polar cap, melting ice directly for water, and maybe even carving out ice caves for habitats. The polar landscape is starkly beautiful, rolling fields of white stretching out to the horizon, under a sun that moves in a low circle around the sky. But then comes the polar night, months of darkness and deep cold when the sun disappears entirely. Any colony there would need to endure a long, frigid winter when temperatures plunge far lower than typical mid-latitude nights and solar energy vanishes. It would be like a combination of a Martian winter and the dark of Arctic winter on Earth, a formidable double challenge. Others imagine a site inside a large crater closer to the equator. Craters like Gale or Jezero, famous for their past lakes and rich sediments, offer scientific treasure troves. Settling in such a place would let colonists live right where ancient rivers once flowed, giving easy access to study any potential fossils or biosignatures left in the clay. A crater base might benefit from the surrounding crater rim, which could block some winds and maybe keep the area slightly warmer at night, akin to a bowl holding heat a bit longer. But building on a crater floor means contending with uneven terrain, possible flash floods of cold air, and the difficulty of climbing in and out over the rim if one wants to travel. It's like choosing to live at the bottom of a valley, scenic and sheltered, but a bit isolated. Jezero, for instance, has stones and delta deposits that could be great for study, but also an obstacle course for landing and roving. A colony there would probably prioritize science over ease, accepting trickier landings to live among scientifically priceless rocks. And then there's Hellas Basin, a giant impact crater in the southern hemisphere that holds the title of the lowest elevation on Mars. The floor of Hellas is over 7 kilometers deep relative to Mars's average surface level. In that depth, the atmospheric pressure is nearly double what it is at higher elevations. Still not enough to breathe, but every little bit counts. More air means landers can use parachutes more effectively, and engines don't have to fight vacuum as much in the final landing phase. Hellas also tends to be a bit warmer at the bottom than surrounding highlands, and sometimes fills with hazes or fogs of CO2 in winter that could be sources of frost. The trade-off? Hellas is something of a dust trap. It's known for spawning dust storms that can then billow out across the planet. If you set up in Hellas, you might have to deal with frequent dust in the air and on every surface. But picture a colony in the center of this enormous basin, ringed by distant high crater walls, a sea of dust and rock around it. The sky might have a permanent slight haze from dust, and sunsets could be especially vivid as light scatters through the particles. Each potential site on Mars comes with trade-offs, a mix of risk and opportunity. No single location gives everything one could want. That's why the decision is so critical. Years before any rocket leaves Earth with colonists, scientists, and engineers will pore over maps and data, debating the merits of Arcadia Planitia's ice versus a lava tube's shelter, or a polar base's water versus an equatorial base's sunlight. They will simulate landings on computer models of terrain, estimate how many kilograms of water could be extracted per day at Site A versus Site B, and study weather patterns from orbit to see which area has clearer skies. It might well be the most important real estate choice in history. In the end, suppose a decision is made. After all the debate and analysis, a particular spot on Mars is chosen as the place where humanity will plant its flag and build its first off-world settlement. Imagine being in the room when that decision is finalized, a group of people pointing to a location on a high-resolution map of Mars, saying, "Here, this plain, or this canyon, or this crater, this will be our new home." It would be a solemn, exciting moment. With the site selected, every preparation narrows its focus to that destination. Cargo landers are aimed specifically for that locale. Engineering plans adapt to the quirks of that terrain and environment. The abstract dream of a Martian city becomes more concrete. A set of coordinates, a landscape that can be visualized and studied in detail. Now the great task becomes turning an empty Martian spot into a living, breathing settlement. The blueprints come out. The designs for habitats, power systems, life support, all tailored now to the chosen site. With the where answered, attention shifts to the how. How do we bring a city to life on a cold, distant planet? What should the first buildings be made of, and how will we get them there? How do we expand from a tiny base to a bustling little town under alien skies? The challenge is immense, but step by step it can be met. With a location set and the first missions planned, humanity stands on the brink of its next giant leap, taking the vision of a city on Mars and crafting it into reality, one piece at a time. The day will come when human boots press into Martian soil at that chosen site, and the work of building a city truly begins. At first, it won't look much like a city at all, more like a small encampment in a vast, silent desert. The first crew will likely step out onto a flat patch of ground, not far from the hulking shell of the lander that brought them. Perhaps their landing site is marked by the scorch of retro rockets on the reddish dust, and the craters, their ship's legs pressed into the ground. In the thin, cold air, these pioneers move deliberately, each step a testament to years of training and centuries of dreaming. They unload the essentials: habitat modules, power generators, rovers, and tools. Every item has its place in the plan. Every action is part of a carefully rehearsed sequence. Before leaving Earth, engineers spent countless hours designing these first shelters. They had to be light enough to launch, strong enough to withstand the jolt of landing, and reliable enough to keep humans safe in an alien environment. The initial habitat might be a stout cylindrical module with thick composite walls, its interior packed tightly with equipment. Within hours of arrival, this module is activated and becomes the first home on Mars. Airlocks clicking, life support humming, a warm light glowing from a porthole into the Martian twilight. The crew will likely connect cables from their lander or a power unit to electrify the habitat. They'll carefully check that oxygen is flowing, that filters are working, that no leaks threaten their fragile bubble of life-supporting air. If the mission planners were able to send cargo ahead of time, there might already be supplies waiting. Perhaps a pre-landed reactor or solar array a short distance away, already unfolded and collecting energy. Maybe a cache of food and spare parts delivered by an unmanned craft in a previous window. Robotic rovers could have been dispatched months earlier, tasked to begin basic site prep, clearing a flat area, perhaps ploughing up some soil to test for ice. Now the humans join the robots in earnest. Working together, they deploy a field of solar panels, angling them toward the sun and dusting them off as needed. They set up a small nuclear reactor brought along for reliable power, situating it a safe distance away and shielding it with Martian dirt. They unfurl antennas and communication dishes to re-establish a strong link with Earth, enabling the two planets to talk, even as one day's journey now separates them by millions of miles. Living quarters might be inflatable. Imagine a large, fabric-sided dome or tube packed tightly during transit, now expanded with air like a gigantic high-tech tent. One crew member oversees the inflation, making sure the material unfolds correctly. Another begins using a bulldozer-like robot to shovel Martian soil against the base of the habitat, piling it up along the sides as a berm. Over the coming days, they might cover more of it, until the inflatable habitat is surrounded by a protective blanket of sandbags or soil. Mars's own dirt turned into a radiation shield and windbreaker. Inside that habitat, a shirt-sleeve environment is slowly taking shape. The air is a mix of nitrogen and oxygen, warmed to sweater weather temperatures and kept at a comfortable pressure. The first night on Mars, the crew might finally remove their suits inside this shelter and breathe freely, the air tasting slightly metallic or plasticky from new machinery, but wonderfully breathable. It will be the first time humans breathe Martian-made air, processed through their life support, while standing on Martian ground. In the beginning, everything is modest and utilitarian. The city is little more than a base camp, a couple of habitat modules linked by pressurized tunnels or connectors, a power supply, some equipment shelters, and perhaps a vehicle garage. Outside, the scene is one of sparse essentials amid an endless expanse of rock and dust. A tall, thin mast might hold cameras and weather sensors to keep watch on the elements. Stacks of crates and reserve oxygen tanks sit secured against the ground. A rover is parked nearby, its solar panels folded like a sleeping insect. When the crew ventures beyond their immediate perimeter, they do so in pairs or more, voices crackling over the radio as they carry beams for another shelter or unroll wiring for additional lights. As the base stabilizes and the days turn into weeks, attention shifts from mere survival to making this outpost a sustainable home. The crew, with help from Earth, plans out the next structures to build. Now it's time to use the resources of Mars itself. One of the first indigenous tasks might be digging into the ground in search of water ice. A robotic drill or a simple heating probe is driven into the soil at a promising spot identified from orbit. Soon, precious water vapor is being extracted from the ground and condensed into liquid water. Proof that Mars can directly provide a lifeline. In a small workshop module, there might be a 3D printer already set up, loaded partly with Martian sand and partly with special binding polymers brought from Earth. This printer could begin crafting bricks or panels from the local soil, slowly building the pieces for a new structure, layer by layer. Nearby, an oven-like device could sinter regolith, heating it into solid ceramic-like tiles that can be used for paving or radiation shielding. Bit by bit, the base grows. After some months, a second habitat module, brought on the initial mission or sent separately and landed nearby, is added. The crew connects it via a tunnel to the first, doubling their living space. This might become a dedicated life support hub or a science laboratory. Using the materials produced on Mars, they construct a low wall around part of the camp as a windbreak, or lay down a stable dirt road between the habitat and the landing zone to make hauling supplies easier. Seeds brought from Earth are planted in a greenhouse module. Under the glow of LED lamps, the first sprouts of lettuce and radishes push up in hydroponic trays, fed by water from Martian ice, and nutrients that might include processed Martian soil components. It's a small garden, but it represents a huge leap. Life growing and being sustained on Mars soil under human care. At the heart of the settlement, the life support systems quietly do their work. A machine hums as it pulls in the thin Martian air, rich in carbon dioxide, and splits those molecules to create oxygen. This may have started as an experiment on a rover years earlier, but here it operates at a larger scale, filling tanks with oxygen for breathing and stockpiling nitrogen and argon, also extracted from the Martian air, to keep the habitat mixture stable. Water recyclers gurgle as they purify every drop, every exhaled breath, every bead of sweat, every used dishwater is reclaimed so that precious water circulates almost closed loop through the habitat. The colony's design might include contingency, perhaps a large dome or bladder filled with reserve water, doubling as both storage and a radiation shield if placed atop living quarters. Inside the habitats, life slowly takes on a routine. Mornings might begin with a gentle alarm and lights brightening to simulate an Earth sunrise for the crew's circadian rhythm. In a common area, no bigger than a small room back on Earth, they gather around a table to have breakfast. Rehydrated foods, maybe a few fresh herbs or salad leaves from the greenhouse to add a burst of flavour. They discuss the day's plans, which equipment to check, what science experiments to run, what construction task to continue. These internal spaces, though compact, are thoughtfully designed to keep spirits up. Perhaps the walls are decorated with a mural of Earth's blue sky, or family photos sent digitally from home and printed out. There could be a small speaker playing soft music, and a digital window that shows the outside view, or even simulates a beach scene from Earth when the crew wants a psychological boost. Every few days, they might have a video call with mission control, depending on the communication delay, sharing news and receiving instructions, or just friendly faces from Earth on a screen. After the initial crew's tenure, which might be 18 months or longer, another mission arrives with new members and more supplies. Over time, the population might grow from that first handful to a dozen or more. With more hands to work, the outpost can expand faster. New modules delivered by subsequent landings are dragged to the main hub and attached like adding new rooms to a house. Perhaps one is a dedicated medical unit with a small sick bay and surgical capability. Another might be a larger greenhouse, broad enough to grow dwarf fruit trees or a wider variety of crops. The settlement begins to stratify. A section for living quarters, a section for labs and workshops, an area for storage and maintenance. Year by year, what started as a tiny camp begins to resemble a village. The power network is reinforced. More solar panels are arrayed over a wider area, glinting in the sun, and connected by buried cables to prevent accidents and reduce exposure to storms. Battery banks or other energy storage systems are expanded to hold enough charge for long sunless periods. If the base is fortunate, perhaps a larger reactor is shipped in on a later cargo lander, providing a stable power supply that frees the settlement from worry about nightfall or dust storms altogether. With ample power, new possibilities open. Maybe an electric press or foundry can start extracting metals from the Martian soil, or an automated chemistry lab can produce plastics and other materials using Martian resources. This means the colony can fabricate spare parts or build tools on site, rather than waiting for the next Earth shipment. If the settlement is in an open plain, the colonists might construct berms or barriers around it to serve as shields against the prevailing winds and to contain their area from roaming dust. Over time, they could even scoop out a shallow moat or ditch to trap drifting sand before it piles against habitat walls. If the settlement was built near or inside a lava tube, Expansion might involve sealing larger sections of the cave and pressurizing them, or drilling small shafts to the surface for additional entrances and light. The physical layout of the town develops a character. Perhaps a main thoroughfare emerges, a packed dirt path lined with flag-like markers, or lights that leads from the original landing zone through the cluster of habitats and over to the storage depots and power stations. Along this path, one day, there might be a plaque or a sign. Mars Base 1, established 2020, reminding everyone of that historic beginning. As architecture becomes more ambitious, colonists attempt structures that earlier seemed like dreams. For instance, they might deploy a large, transparent dome over a flat area to create an indoor courtyard or park. This dome could be made of multiple layers of strong plastic and glass, shipped in sections and assembled on Mars, then reinforced with 3D printed struts. Once sealed and pressurized, it becomes a shirt-sleeve environment, perhaps the first place on Mars where people can walk around without suits, albeit within the confines of the dome. Inside, they might lay down gravel paths, set up benches, and plant hardy plants brought from Earth that thrive in low light or low pressure. Imagine an astronaut, after a long day's work outside in a suit, stepping into this dome and taking off their helmet to feel fresh, moist air and see a small tree or a patch of green grass underfoot. It would be a little oasis of Earth on Mars, a powerful reminder of what they're working to achieve on a larger scale. The settlement also sets up systems for the long term. Perhaps there's a large excavation a short distance away, where they plan to build a more permanent habitat, partly underground. They could use explosives or heavy drills to carve out a pit, then line it with bricks baked from Martian clay, eventually putting a dome or roof over it and covering it with soil, a hybrid between a building and a bunker. This could become a larger habitation block or storage warehouse. In some corner of the outpost, an array of antennas and dishes grows taller, communication towers to not only talk with Earth, but also maintain links with any satellites or other bases that might come in the future. The city planners, for by now there is need of planning, organize the layout so that as more modules arrive, they know exactly where the next ones will go, ensuring efficient connections for power and life support. They leave clear zones for emergency evacuation paths or landing clearances, learning perhaps from near-miss incidents as they go along. Though at this stage the settlement may still consist of only dozens of people, the goal is always to design for the future, hundreds, perhaps thousands of inhabitants in time. So the blueprint evolves. What began as a sketch of a base becomes a detailed town plan. There might be mapped locations for a future hospital, a larger life support farm, maybe even separate neighborhoods or clusters if the population grows. The architecture might start reflecting a sense of community aesthetics too, not just functional placement of modules, but thinking of how to create a sense of home. Perhaps they paint the habitat exteriors in different colors using Martian pigments, or set up flags and symbols of the Earth nations or organizations that contributed. A communal gathering hall could be fashioned by linking a few big, inflatable modules, where the whole group can meet at once for meals or discussions, something the first crew couldn't dream of when they ate in shifts in a cramped galley. Still, in these early stages, the city is humble. As the sun sets one evening, an observer standing on a nearby rise would see a cluster of domes and cylinders, some half buried, some covered in dust, arranged in a rough circle connected by tubular walkways. Lights from inside cast a warm glow through small windows or transparent sections, shining onto the rusty ground. A lone antenna blinks a red light. Beyond the perimeter, darkness envelops the endless Martian land, cold and indifferent. But here, in this small circle of life, is a triumph of human spirit and perseverance. From orbit, if you knew exactly where to look, you'd spot a tiny glimmer, this outpost's lights, merging into a golden pinprick against the deep blue of Martian twilight. The blueprint that was once lines on paper is now reality, step by careful step. Challenges continue, of course. Every addition to the city needs more resources. Every increase in population means life support must be scaled up. There will be setbacks, a critical system that needs urgent repair, an unexpected dust storm that lasts longer than anyone predicted, perhaps health scares as bodies adapt to this new world. But each challenge is met by a community growing in confidence and capability. They innovate solutions on the fly, often sharing them with Earth for analysis, and in return, Earth sends new ideas and encouragement back. In time, the colony passes a threshold. It generates enough of its essentials, water, air, food, power, that it could survive on its own for a while if it had to. That is a day for quiet pride. Now imagine, years from that first landing, standing in the heart of this Martian settlement during a moment of rest. Perhaps it's night, and the crew, now a small society, has gathered in the domed common hall to mark an occasion, a holiday from Earth, or the anniversary of their landing. Someone plays a gentle tune on a makeshift guitar that made the journey out. A few people sway or dance in the lower gravity, laughing at the lightness of their steps. Others pass around cups of rehydrated coffee, or perhaps a treat baked from the colony's first wheat harvest. Faces of many ethnicities and backgrounds are around you. Humanity is represented in this brave little outpost. There might be a short speech, remembering those who dreamed and worked to make this possible, including those millions of kilometers away who gaze up at the night sky and think of the people on Mars. Afterward, stepping outside in a pressurized rover or suit, you see the settlement settled into the landscape like it belongs there. Above, the stars are starting to fade as Mars's pre-dawn light grows. On the horizon, there's a cool glow, perhaps Phobos, the closer moon, rising swiftly before dawn, or maybe just the first blue hint of sunrise. The lights of the habitats twinkle in the dim morning, and you think about how extraordinary it is that not long ago, this place was as untouched as any in the universe. Now it's touched by life and ambition. We leave the city here, poised between its challenging present and its promising future, as the first faint rays of the sun peek over the Martian horizon. In the coming dawn, the people of this fledgling city will wake and resume the work of living on Mars, solving problems, sharing stories, pushing boundaries. Each day, they survive and thrive. The once distant vision of a city on Mars becomes more solidly real. And as we imagine this scene, lights in the Martian night and human voices where once there was silence, we feel the gentle thrill of a dream becoming history. The red world, which for ages was only a whisper in our night skies, now hosts our footsteps and our shelters. It is no longer just Mars. In a small but profound way, it is ours. Under two small moons, on a cold and quiet morning, a new chapter of humanity begins, awaiting the full sunrise of all that is yet to come. In the pre-dawn darkness, a lone rocket stands tall against a starry sky at the edge of a silent coastal plain. Inside the capsule perched atop this metal giant, the crew sits strapped in, their breaths echoing softly in their helmets. The countdown clock ticks steadily, each number bringing them closer to an irreversible moment. When ignition comes, it comes quietly at first. A distant tremor, a growing vibration as the engines roar to life far below. Then the deep rumble builds, and the ground brightens in a sudden dawn of flame. Slowly, ponderously. The rocket ascends on a pillar of fire, its light painting the low clouds gold as it climbs. The crew feels the weight of acceleration pressing them into their seats, yet a calm focus holds them. They have trained for this, and they ride the controlled fury with quiet awe. The thunder of launch is muffled in their ears. Through their vibration-dancing windows, they watch the atmosphere glow and then fade to black as they push toward orbit. Minutes later, engine cut-off comes, and weightlessness gently envelops the crew. They have arrived in Earth orbit. Outside their windows, the curve of the blue planet stretches beneath a veil of white clouds, achingly beautiful and fragile. There is a hushed moment of realization. They have left their home world behind, trading the pull of gravity for the endless fall of orbit. Yet their journey has only begun. Over the next days, heavy boosters thunder upward, one after another, delivering additional cargo and propellant to join them in orbit. In total, dozens of launches are needed to assemble and fuel the Mars-bound craft. Uncrewed tanker vehicles rendezvous with the crew's ship, docking with slow precision to transfer propellant for the transplanetary voyage. The crew watches through viewports as silvery tanks offload their liquid methane and oxygen, the fluids drifting weightlessly through hoses between vehicles. Piece by piece, their interplanetary convoy is prepared for departure, all while Earth's blue crescent drifts silently below. The departure must be timed precisely. Earth and Mars align favorably for such a voyage only about once every 26 months. For a short while, the assembled spacecraft coasts in orbit as mission controllers run final checks and the planets inch into the right position. Then comes the moment for the Trans-Mars injection burn. In a final crescendo, the spacecraft's engines ignite again, burning steadily for several minutes to break free of Earth's embrace. The crew feels a prolonged, gentle push, and through their window they see Earth begin to shrink. The engine roar fades to silence once more. In a matter of hours, their home world becomes just a bright blue star in the dark. They have left Earth behind. Ahead lies the open sea of space and the faint, beckoning presence of Mars. There is no turning back now. Now free of Earth's gravity, the crew's entire world is the spacecraft itself, a self-contained ark designed to sustain them during the long voyage between planets. The heart of this ship is its habitat module, a cylindrical living space several meters across with multiple levels for work and rest. Every surface inside is put to use. The walls are lined with equipment panels, storage lockers, and Velcro patches anchoring all manner of gear. Handholds and tethers dot the corridors to help the crew float from one section to another in weightlessness. There are snug, private sleeping berths for each crew member, a compact galley where they prepare meals, and even a small greenhouse cabinet where a few plants grow under gentle LED lamps. A tiny oasis of green life amid the humming machinery around them. Toward one end of the habitat, a windowed science bay serves as the ship's laboratory. Here the crew can peer at samples through microscopes and perform experiments in microgravity. There is even a 3D printer for fabricating tools or spare parts on the fly. Medical supplies are strapped in place nearby, alongside a small freezer and diagnostic equipment. Despite all the technology, the designers have added human touches to make the space feel more welcoming. Soft, ambient lights mimic an Earth-like day-night cycle. Personal photographs and mementos float gently, taped to the walls at each crew station. A communal pinboard carries handwritten notes, a mission calendar, and perhaps a child's drawing sent along from home. These small comforts remind the astronauts of life beyond the hull, keeping them connected to their humanity as they voyage onward. For propulsion, the ship relies on a cluster of powerful rocket engines, fed by the methane and oxygen fuel it topped up in Earth orbit. In deep space, these engines will only fire occasionally, for course corrections or the critical burn upon reaching Mars. The bulk of the journey is an unpowered coasting along an invisible path plotted by orbital mechanics. Unlike missions of the past that would drift for 6 to 9 months to reach Mars, this expedition is taking a faster trajectory. By expending more energy up front and optimizing their route, they aim to reach Mars in roughly 3 months' time. This shorter transit not only hastens their arrival, it also means significantly less time exposed to the hazards of space. The engines and navigation systems have pushed the envelope of what chemical propulsion can do, allowing the crew to traverse the 300 million kilometer gulf more quickly than anyone before. During most of the cruise, the engines lie dormant, and the ship glides silently through the void, a steel life shell carrying its sleeping fire, ready to be reignited when needed. Despite its comforts, the ship remains a fragile bubble in a hostile void. Beyond its walls, cosmic rays and solar radiation constantly bombard the vessel. To protect the crew, the spacecraft's design uses every available material as a shield. Water tanks and fuel stores are positioned around the living quarters to absorb radiation, and the hull incorporates hydrogen-rich polymers that blunt some of the high-energy particles. Should the sun erupt with a solar storm, the crew can shelter in a small, heavily shielded compartment, a dedicated storm shelter lined with extra hydrogen-rich mass to reduce their exposure. But not all dangers can be so easily stopped. The steady drizzle of galactic cosmic rays penetrates even the best shielding, delivering a slow accumulation of dose throughout the voyage. Mission planners accept that some radiation exposure is unavoidable. Instead, they have minimized risk by shortening the trip's duration as much as possible. Over a 90-day transit, the crew will receive on the order of a few hundred millisieverts of radiation, significant, but still below the strict career limits set for astronauts, and roughly half of what a 6-month voyage would have entailed. Each day, in deep space, the ship carries them through this invisible shower, and each day, their protective measures and careful planning keep them safe for the world that awaits. Life between worlds settles into a steady routine. In this isolated micro-world, the crew relies on sophisticated life support systems to keep them healthy. Air, water, and even waste are continuously recycled to conserve supplies. Every exhaled breath is processed. Filters scrub out carbon dioxide and trace contaminants. Then fresh oxygen is added to replenish the cabin air. That oxygen often comes from splitting water molecules. An electrolysis unit quietly produces O2 for the crew to breathe and vents the excess hydrogen overboard. Water is equally precious. A network of pumps and filters collects moisture from the air, exhaled breath, sweat, even tears, and purifies it back into liquid for use. The system recycles urine as well, reclaiming it into clean water. In fact, up to 90% of all water used on board is recovered and reused, a vital efficiency when every drop carried from Earth is so costly. The result is a nearly closed-loop ecosystem, a delicate balance of chemistry and engineering that sustains life in the vacuum of space. Food, however, cannot be recycled in the same way. The crew subsists on a pantry of shelf-stable provisions packed before launch, dehydrated vegetables, freeze-dried meals, and vacuum-sealed packets of grains and proteins. Cooking is minimal. There is no open flame or stovetop here, only a small electric food warmer and a hot water dispenser to rehydrate meals. Still, gathering at mealtimes provides structure and a sense of normalcy. Occasionally they open a treat reserved for morale, perhaps a packet of real coffee, or a special dessert brought for a birthday or holiday. These small comforts break the monotony. Once a week, they even harvest a handful of fresh lettuce or herbs from their little hydroponic garden to add a crisp, peppery bite to their dinner, an immeasurable boost to taste and mood. One crucial part of the daily routine is exercise. In microgravity, without weight bearing, the human body rapidly begins to weaken. Muscles atrophy and bones lose calcium. To combat this, each crew member devotes at least 2 hours a day to physical exercise. The spacecraft's small gym area is equipped with a stationary bicycle and a treadmill that can be used with harnesses to keep the runner's feet on the belt. Most importantly, there is a compact, resistive exercise machine that simulates weightlifting, a technology first tested on the International Space Station to maintain astronaut strength. This advanced device, only about 65 pounds in mass, can provide up to 350 pounds of resistance for lifting exercises. The crew use it for squats, deadlifts, and presses, straining against piston-like rods to stress their muscles and bones. As an added benefit, the machine even harnesses the energy from their workouts, feeding a bit of electricity back into the ship's power system. Through these daily regimens, the crew keeps their bodies as strong as possible, knowing they will need muscle power and endurance when they arrive, and must work in Mars's gravity again. Just as important as physical health is mental well-being. The voyage is long, and the confines of the ship are small. Maintaining a positive, focused mindset is a deliberate effort. The crew follows a structured daily schedule provided by Mission Control, but they also adapt it to their own pace. Each morning, as defined by the ship's clocks, they confer on the day's plan, periods for exercise, for equipment maintenance, for research tasks, and periods for rest or leisure. This structure provides a sense of normalcy and purpose. It also helps stave off monotony and aimlessness. In past isolation studies, crews that lacked routine grew sedentary and demotivated, so these astronauts guard against that by keeping each day patterned. They also intersperse variety, rotating who does which chore, planning special activities on certain days, and giving everyone personal time to break up the sameness of months in a tin can. For instance, during the journey, they make it a point to mark personal milestones and holidays together. They celebrate each crew member's birthday with as much festivity as they can muster. On one such evening, lacking the means for a real cake, they improvise. A tortilla spread with a sweet paste stands in for cake, and a tiny flame drawn on paper stands in for a candle. They sing happy birthday, softly, into a microphone for a video message home, and share a pouch of chocolate pudding as a treat. These improvised celebrations, though simple, bring laughter and cheer, breaking up the long weeks of travel and reminding them of life back home. On Sundays, they lighten the workload, allowing a few extra hours for personal projects, or simply gazing out the window at the stars. Such rituals become important markers of time, giving the crew things to look forward to and a sense of progression. Even with busy schedules, there are still quiet hours that must be filled. The crew finds solace in small pleasures. They have a digital library of books and movies. Many evenings, one of them floats near a window, reading a favourite novel on a tablet, while another might watch an old movie on the laptop strapped to the wall, the sound turned low to avoid disturbing others. They talk about their families, their dreams for the mission, and sometimes they simply joke around to lift spirits. They send recorded video messages to loved ones whenever communication windows allow, knowing that their words will take many minutes to reach Earth, and the replies longer still. Conversation with home isn't in real time, but hearing a familiar voice in a recording or reading an email from a spouse provides comfort and motivation. Sometimes, an astronaut will steal a moment at the observation port to simply stare at the stars. Far from Earth's city lights, the view is breathtaking. A dense spray of stars unblinking in the blackness, and the hazy band of the Milky Way crossing the sky. By now, Earth itself is just one of those twinkling points. The crew knows which one. They occasionally spot the pale blue star that is Earth, and perhaps nearby the faint glint of the moon tagging along. Seeing it, they feel both a pang of homesickness and a renewed determination for why they are out here. In the opposite direction, the crew can now discern Mars as well, no longer just a dim red dot, but a growing disk with hints of ochre and white. Each day, it looms a little larger. In these reflective moments, floating in the quiet cabin with their crewmates, either busy or asleep, an astronaut can feel truly the vast distance from everything they've ever known. And yet, they do not feel alone. They have each other, and beyond that, an entire planet of people pulling for them. This thought becomes a comfort on the long journey. Every day out here is one step farther from Earth and one step closer to Mars, and they savor the journey as much as the destination. After long months in transit, the day finally arrives when Mars is no longer a distant dream, but an imminent reality. The bright red dot has grown into a rusty orange orb, filling the window, detailed with faint brownish patterns and swirls of white cloud. There is excitement and a touch of anxiety in the crew's voices as they make final preparations for arrival. They have gradually adjusted their trajectory over the past weeks to aim for the selected landing site on Mars. Now the ship is approaching the planet on a precise course. The crew secures loose items, straps themselves into their acceleration couches once more, and runs through the entry and landing checklist that they've practiced so many times. Each astronaut dons their heavy launch and entry suit, sealing themselves in and checking their comlinks. This will be a one-way descent. There is no orbit insertion burn to gradually ease them in. They are coming in directly. All eyes turn to the flight displays as Mars grows larger and larger. The spacecraft's guidance system executes a final course correction burn, just a nudge to fine-tune the angle of entry. The crew feels a small push as thrusters fire, then it's done. They are on the exact path that will intersect Mars' atmosphere at the targeted entry point. The ship reorients itself, rotating to put its broad heat shield forward like a giant cosmic umbrella. All systems are nominal. The commander calls out to verify that each crew member is ready. They respond with calm, clipped affirmatives. Though their hearts are racing, training kicks in. This phase is critical and demands concentration. Through the windows, they can now see the upper atmosphere of Mars, a thin haze along the planet's curve, approaching fast. The craft automatically switches to entry mode. Entry interface in 1 minute, a crewman announces. They tighten their harnesses and grip their armrests lightly. One astronaut steals a quick glance at a small photo taped inside her helmet, a family portrait, then focuses on her display. The capsule begins to vibrate ever so slightly as the fringes of Mars's atmosphere whisper against it. Soon, the tenuous upper air of Mars greets the speeding vessel. At first, the sensation is gentle, a slight buffeting. The ship's altitude starts to plunge rapidly. Within moments, the resistance intensifies. The hull starts to shake, and a dull roar grows outside as the air molecules, so scarce yet coming so fast, slam into the heat shield and compress into searing plasma. Through their small side windows, the crew sees a fierce glow building, envelopes of incandescent gas in orange and pink, licking past the heat shield's rim. Inside, the temperature remains cool, but they can feel the quiver of turbulence and the onset of deceleration pressing them into their seats again. One astronaut grunts softly. A few moments later, another calls out, "Max G," letting everyone know they're hitting the peak forces, and then it should ease. They ride through a firestorm. Outside, the temperatures on the heat shield spike above 1,000 degrees Celsius, and a tail of glowing plasma streaks behind them like a shooting star. Telemetry to Earth becomes garbled and then cuts out. The ionized gas around the spacecraft blocks radio signals. For several minutes, the crew is on their own, plunging through Martian skies with no communication except with each other. Mars's atmosphere is doing what it can to slow them, but it is a thin agent. Unlike Earth's thick blanket, Mars's air is over 100 times thinner. Even so, it has succeeded in stripping away a vast amount of their velocity. The spacecraft has decelerated from nearly 20,000 kilometers per hour to a few thousand in the span of minutes, universetoday.com. The scream of entry gradually lowers in pitch. The most violent part of the ride smooths out as the capsule drops into denser, though still very thin, layers of air. The plasma sheath fades, communication static dissolves, and presently the ship's radio can be heard again by anyone listening. A crew member reports, a bit breathlessly, "Entry phase nominal. We're through the peak." There's a collective silent sigh of relief, but they all know the most critical phase lies ahead. The vehicle is still hurtling downrange at several times the speed of sound, and Mars's surface is racing up to meet them. There is too little atmosphere here to come to a stop by aerodynamics alone, universetoday.com. Now comes the heart-stopping maneuver that will make a human landing possible. As the ship descends into the lower atmosphere, its guidance system takes over for the final approach. The onboard computer pitches the capsule to bleed off horizontal velocity and then signals the next sequence. In an instant, explosive bolts fire and jettison a pair of forward flaps, and the ship's main engines ignite while the vehicle is still traveling supersonically. A daring feat. A thunderous reverberation booms through the thin air as multiple rocket nozzles come to life, their flames blasting forward against the direction of travel. This is supersonic retropropulsion, a technique first proven on Earth by experimental booster landings and now being used on Mars to slow a heavy crew vehicle. The crew feels a dramatic jolt as the rocket's thrust fights the residual momentum. The view out the window, once a blur of reddish clouds, steadies. The capsule's descent vector shifts. It is no longer just falling, it is flying, under power, slowing down rapidly. A great cone of exhaust gas pushes against the Martian air, creating a shockwave and billowing turbulence visible as dust ripples below. Inside, the G-forces which had eased now build up again in the opposite direction, deceleration from the rockets. The astronauts are pressed forward in their harnesses momentarily as the autopilot adjusts the engine throttles to find the perfect balance. Through the front-facing windows, the crew can now see the dusty Martian surface coming into clearer view. They're descending into a sky of salmon-pink haze, with the ground features sharpening from indistinct colors into actual rocks, slopes, and plains. A voice calls out altitudes. Velocity 800 meters per second, 600, 400. Still supersonic, but rapidly dropping. The retropropulsion burn has done its job well. In mere tens of seconds, the vehicle has shed the majority of its remaining speed. As it passes through the speed of sound, a double sonic boom cracks across the Martian desert, heralding the arrival of humanity, with echoes rolling over the distant hills. The ship's computers now pivot it into a vertical orientation, engines downward. What was a capsule-shaped entry vehicle has reconfigured into a vertical lander, more like a tall rocket. The main engines briefly shut off, having done their big burn. Now smaller, throttleable thrusters take over for the final approach. The crew has a moment to register their surroundings. Out of the viewport appears a rust-coloured landscape of surprising beauty. They glimpse the landing area, a broad, flat plain mottled with rocks and dust, with hills or crater rims far in the distance. Sunlight angles in, tinting the ground a reddish gold. 300 meters, calls the commander, reading instrumentation. The craft is now descending at a few tens of meters per second, engine thrust balancing Mars's gravity in a controlled drop. The astronauts feel almost weightless again for a brief moment as the thrust to weight evens out. Peering outside, they can discern individual boulders and the texture of the terrain. A shadow grows more defined beneath them. Thin wisps of dust swirl upward, kicked by the gentle pre-landing thrusters. At 100 meters above the surface, the landing radar locks onto the ground. The onboard system makes rapid decisions, firing brief bursts from side thrusters to nudge the trajectory slightly and avoid any hazardous-looking rocks below. The crew holds their breath, heartbeats quickening. Despite the automation, these final seconds are tense. 50 meters, 20, 10. A sudden burst from the main engines kicks up a reddish cloud as the vehicle arrests its descent. The cabin rattles softly as dust grains pepper the hull. Through the obscuring dust, the astronauts sense a gentle bump, a slight lurch upward that quickly settles. A pause, and then, touchdown confirmed. The words ring in their helmets. For a split second, there is silence. The engines have cut off, the sudden stillness almost deafening after so much noise. They have made it. The spacecraft rests on its landing legs on Martian soil. Inside the cabin, the crew exchanges astonished, exhilarated glances. There's a collective exhale as the realization sets in. After a journey of hundreds of millions of kilometers and a harrowing descent through thin air, they are safely on Mars. One astronaut lets out a little laugh that sounds more like a sob. Another grips her crewmate's arm with a gloved hand in congratulations. Outside, the dust cloud begins to drift and settle, revealing a sky turned a muted pink by suspended fines. The lander's shadow lies stark on the ground. Systems across the board report nominal. The vehicle has shut itself down into post-landing mode, and the cabin pressure remains stable. The crew remains seated for a few minutes, running through post-landing checklists almost on autopilot, still absorbing the magnitude of what has just happened. They are on another planet. Through the small triangular window at the hatch, a hazy vista emerges as the dust clears. The landscape of Mars, serene and alien, bathed in the light of a late Martian afternoon. The commander unstraps and carefully stands up, his body trembling slightly with adrenaline. Take it slow, he reminds everyone. They have arrived, but the mission is just beginning. As the dust outside gradually settles, a new scene comes into view around the lander. The crew peers out, eyes pressed to the thick glass of their portholes. They can already see that they are not alone here. Scattered on the Martian landscape are machines and structures that have preceded them, the fruits of missions that arrived months or years earlier to prepare this moment. Not far from the lander, a squat wheeled rover is parked atop a rise, its camera mast pointed in their direction as if in welcome. Beyond it, a cleared expanse of ground can be made out, conspicuously flat and free of large rocks, marked by geometric patterns on the surface. And a few hundred meters away, a cylindrical dome with shiny fabric walls sits patiently, the habitat module that has been awaiting their arrival. Mars is not an empty canvas. Their robotic vanguard has already sketched the outlines of humanity's first foothold on the red planet. Long before the crew's descent, autonomous robots had been hard at work on this beachhead. One heavy rover, effectively a robotic bulldozer, spent weeks grading and compacting the soil at the chosen landing zone. Using Martian regolith itself as construction material, it baked and assembled a rudimentary landing pad out of interlocking basalt bricks, creating a stable platform for touchdown. This prepared pad meant that moments ago, when the crew's vehicle descended on its engines, it kicked up far less hazardous dust and debris than it would have on raw ground. The flat, reinforced surface also helped ensure the lander's legs found even footing. The robotic builder responsible for this pad now sits off to the side, its job completed. The crew silently thanks this tireless machine for its foundational work. A short distance beyond the pad, the crew can see the metallic gleam of the outpost's power station. This is a compact nuclear fission reactor that was delivered by an unmanned cargo lander over a year ago. Not long after its arrival, robotic arms lifted the reactor unit onto a wheeled cart and trundled it to a safe distance from the main habitat site. There, it was remotely activated to provide a steady source of electricity. Ever since, the reactor, a device small enough to fit in a large closet, has been generating around 10 kilowatts of continuous power, quietly feeding the proto-colony's systems. It kept the habitat warm through frigid Martian nights and charged batteries for the rovers and instruments. Nearby the reactor's location, one can make out an array of deployed solar panels as well, glittering in the dusty sunlight. These were unfolded by robots to supplement power during the daytime. Between the always-on reactor and the solar farm, the site has ample energy. The crew knows that thanks to this setup, they have electricity to run life support, lights, communications, and all the necessities from the moment of arrival. The sight of the reactor's mast and the splayed solar wings is deeply reassuring. But the most heartening sight of all is the habitat module. It stands on the open plain, mounted on its landing base, exactly where it was placed months prior. The habitat is a large inflatable dome structure, covered in layers of protective polymer and insulation. Before the crew launched from Earth, this module was sent to Mars on an automated lander and set up by remote control. Robots triggered the inflation of its soft walls and partially outfitted its interior, and for months it has been under remote supervision. All critical systems were tested and found to be functional in advance. The crew recalls hearing that milestone call while they were still in training. The moment when mission control confirmed the habitat was upright, holding pressure, and alive on Mars with no humans around. Now here it is in the flesh, or rather fabric and metal, their future home on Mars, waiting for them to step inside and truly commission it. Elsewhere around the landing zone are other hints of robotic groundwork. Tracks in the reddish dust crisscross between the habitat, the power unit, and the landing pad. These were made by a pair of smaller rover scouts, which have spent the last few months roving the area to map it in detail. They identified the flattest routes between key points and flagged any dangerous terrain features, like soft sand or sharp rocks, to avoid. One of these rover scouts is visible now, parked on a slight hillock, acting as a communications relay. It likely captured imagery of the crew's landing and beamed it to an orbiter during descent. These robotic scouts also acted as weather sentinels. They monitored the Martian atmosphere daily, measuring wind, temperature, and dust in the air to provide environmental context for the incoming crew. And not all the scouts stayed on the ground. A lightweight helicopter drone also came with the contingent of robots. During the lead-up to the crew's arrival, it made several short flights over the terrain, surveying areas beyond the rover's reach. The drone verified that there were no surprises lurking just over the horizon and gave aerial views of potential science sites. Its contribution is harder to spot from the lander's window, but the crew knows from reports that it performed excellently, proving that powered flight in Mars's thin air is indeed possible. Finally, scattered near the habitat module, the crew can see pallets and packages, supplies that were pre-delivered. These include containers of food, extra water and oxygen, scientific equipment, and spare parts for machinery. A robotic crane on one of the cargo landers had arranged these bundles neatly on the ground for easy access. In addition, an ISRU, in situ resource utilization, experiment has been running. a small plant that pulls in carbon dioxide from Mars' atmosphere and, using hydrogen feedstock sent from Earth, produces methane and oxygen fuel via the Sabatier reaction. Over many months, this automated fuel processor has generated a stockpile of propellant and oxidizer, now stored in bulky tanks beside the landing site. This is fuel intended for the crew's eventual ascent vehicle, or for other vehicles on Mars. By the time the crew landed, a substantial reserve of methane and oxygen had been accrued, a tangible safety net, ensuring that when it comes time to leave Mars, they will have the means to do so. In effect, the robots have already begun living off the land, turning local air and soil into useful resources. All these preparations mean one thing. The crew is stepping into an outpost that is primed and ready. The base has power, shelter, supplies, and functional equipment, all checked and verified by robotic helpers and the engineers back on Earth. The stage is set. As the crew finishes post-landing procedures inside their vehicle, they exchange a look that communicates both excitement and responsibility. Outside their window is a new world and a ready-made haven assembled for them. It's time to go meet it. A short while later, with their spacecraft safely shut down and their immediate post-landing checks complete, the crew prepares to egress, to step out onto Mars for the first time. Donning their visored EVA helmets and life support packs, two of the astronauts make their way into the lander's small airlock at the base of the capsule. The others watch from inside, cameras recording, as the outer hatch is opened. A hiss of equalizing pressure, and then the hatch swings outward. Harsh, dusty Martian daylight floods into the airlock vestibule. The first astronaut in line grips the ladder rails and begins descending slowly. "Take it nice and easy," the commander advises over the radio, his voice measured but tinged with emotion. Boot by boot, rung by rung, the suited figure lowers until his foot hovers just inches above the Martian ground. And then, with a final step, he places his boot into the rust-colored soil of Mars. It presses down lightly, gravity here being only 0.38 of Earth's, and the soil gives way a bit. A small puff of fine pink dust encircles the boot as it settles. "Contact," he says softly. There is no shout of triumph, no quick quip, just that understated word and a voice thick with meaning. A human being is standing on Mars. He takes a moment to steady himself. After months in microgravity, even Mars's gentle gravity feels strange, simultaneously a relief and a challenge. His legs are not weak exactly, the exercise paid off, but the sense of weight and downness is novel. He pauses, letting the slight dizziness pass. Inside his suit, he feels the tug of his body downward and the mild resistance of muscles that haven't carried weight in a long time. Regaining focus, he makes his first careful steps away from the ladder, clearing the path for his crewmate following above. The second astronaut descends and soon steps off the ladder as well, a few meters from the lander. She moves slowly, getting used to the clunkiness of walking in the suit and the low gravity. Each motion is gingerly placed. They both look like divers underwater, deliberate and floating. The landscape around them is breathtaking, a vast expanse of reddish-orange desert stretching to the horizon under a butterscotch sky. Scattered rocks and pebbles lie everywhere, some half buried in drifts of fine sand. In the distance, low hills ring the plain, perhaps the eroded rim of an ancient crater. The afternoon sun, pale and small compared to how it looked on Earth, casts a golden light that makes the terrain glow. The astronauts can see their own long shadows on the ground, mingling with the shadow of their lander. A faint breeze picks up, wafting some dust across the surface in dancing puffs. Even through the suit's insulation, They can sense the chill in the air. The external temperature is well below freezing. The only sounds are the ones they carry with them, the soft hiss of their suit ventilators and the crunch of Martian soil under their boots. Mars itself is silent. No animals, no rustling trees, just an ancient stillness. For a few heartbeats, the two pioneers simply stand and absorb the moment. One turns slowly in place, taking in a 360-degree view of the horizon. The sky above is a muted salmon color, fading to blue-gray near the zenith, a coloration caused by fine dust suspended high in the atmosphere. It's thinner air than their lungs have ever encountered, outside their suits, but visible nonetheless by the way it tints the sunlight. The second astronaut looks down and notices something small and remarkable. Her boot print, well defined in the powdery soil. It strikes her that this impression might last for years, perhaps centuries, in a place with so little wind or water to disturb it. A footprint on Mars. She takes a photo with the camera mounted on her suit's chest. They resist the urge to celebrate too boisterously. They exchange a gloved handshake, a gesture of shared achievement, but their focus quickly returns to the tasks at hand. Mission rules dictate that they get to the habitat module relatively soon to fully secure their life support and begin setting up base. The commander's voice crackles over the radio from inside the lander. "How do you feel out there?" "Solid, boss," comes the reply. "The ground is firm. We're good to go." The two on the surface begin collecting the tools and equipment they brought in the airlock. A portable cart on wheels, some tether lines, and connector cables. Above them, the other two crew members are preparing to follow, but for now, these two will act as pathfinders to the habitat. Their first destination is the pre-deployed habitat module about 200 meters away. They load a few essentials onto the little wheeled cart, spare oxygen tanks, diagnostic devices, and contingency supplies, then start the trek. Walking on Mars is an odd mix of effort and ease. Effort, because the suits are cumbersome, and each step kicks up sticky dust. Ease, because gravity is so low that moving feels like bounding more than trudging. They adopt a shuffling lope, finding a rhythm in the 1/3 G environment. Every few steps they pause to ensure their partner is doing well. This is their first real walk on Mars. Caution comes first. The habitat glints ahead of them, its white fabric skin almost luminescent in the sunlight. As they approach the module, they can appreciate its scale. It's about the size of a large inflatable tent or small house, with a rounded top and rigid base. It rests on a platform that had been leveled by robots. The exterior is pristine, save for a thin film of dust around its lower half, and the shadow of the reactor's mast stretching across the ground nearby. The two astronauts walk around the habitat slowly, performing an external inspection. They check for any signs of damage, meteoroid punctures, tears, or unexpected bulges. All appears exactly as it should. The module skin is taut, its structural supports undamaged. The main airlock door on the side is closed and locked, as it has been since it was tested remotely. Now it's time to bring the habitat fully online. The crew members plug in a thick power umbilical from the habitat to a junction box that leads to the reactor and solar array. While it had basic power, now it receives a full flow of electricity for normal operations. Immediately, lights inside the habitat brighten, visible through a small round window, and systems begin to wake from standby. One astronaut consults a checklist on her wrist display and radios to the orbiting crew and Earth that they are commencing habitat activation. They work through the steps, turning on the habitat's primary heating and ventilation. A low hum from within indicates fans are spinning up to circulate air. Via an external control pad, they command the habitat's life support system to transition from idle to active. Tanks aboard the habitat begin releasing stored oxygen and nitrogen to bring the internal atmospheric pressure up to Earth normal levels. It had been kept at a minimal safe pressure until now. The astronauts watch the telemetry. Inside the habitat, pressure is climbing to 101 kilopascals, oxygen steady at 21%, temperature rising from the maintenance setting of 10 degrees Celsius toward a comfortable 20 degrees Celsius. Everything is proceeding by the book. After waiting a short time for the habitat's environment to stabilize, the moment comes to enter. One of the astronauts volunteers to be the first to go in, while the other remains outside to monitor and assist, a standard precaution. The first astronaut approaches the main hatch. It's a sturdy circular door, marked with both the mission emblem and universal symbols indicating the airlock. He presses the panel to initiate the airlock cycle. With a hiss, the outer door unlocks and swings outward. He steps inside the cylindrical airlock chamber, lugging a duffel of initial supplies with him. The outer door closes behind him, and for a brief minute he is in solitude, the first human in a structure on Mars. The chamber pressurizes to match the habitat interior, which is now at shirt-sleeve conditions. Indicators flash green. With a deep breath of suit-provided air, he's still fully suited for now. He opens the inner door and floats through into the habitat proper. The interior is illuminated in soft white light. He is standing in what looks like a compact but functional living space, not unlike a space station module, but with a homier touch. There are padded light-coloured walls, floor panels, velcroed with tools and straps, and fold-out furnishings still stowed against the sides. The air is crisp and cool, smelling faintly of plastic and metal, new, clean, untouched by humans until this moment. Instrument readouts along one wall show nominal conditions. Pressure, temperature, and gas mix all in the green. He takes a sampling device from his belt and lets it sniff the habitat's air. It confirms what the readouts already say. The atmosphere here is breathable and pure. Habitat is pressurized and stable. I'm inside, and it's beautiful, he radios out. A cheer crosses the communications net, from his crewmate outside, from the two still in the lander, and from distant mission control on Earth, though he won't hear Earth's reply for many minutes. Step by step, he goes about verifying that all is in order. He checks the hatch seals for both doors, examines the interior for any damage that might have gone unnoticed, and powers up the habitat's internal console. All systems are nominal. He can hardly contain a grin as he reports that everything looks great. "Copy that," his partner outside replies, a smile evident in her voice as well. Proceeding to ingress. Moments later, the airlock cycles again, and the second astronaut enters the habitat. The two help each other remove their helmets and gloves. For the first time, humans breathe the air of a Mars habitat. It feels fresh, cool, and wonderfully abundant after the confines of their suit. They both take long, deep breaths and then laugh. "It's better than Earth, because it's Mars air, our air," one jokes. They peel off the upper parts of their suits, leaving the lower torso assemblies on until the rest of the crew comes in to help with those. It's a surreal experience. They are standing in ordinary coveralls, face to face, inside a structure on Mars, casually breathing. This dome of safety, maintained by human technology, is an oasis in an otherwise deadly environment. The remaining two crew members soon join them, bringing in additional gear through the airlock. Within an hour of landing, all four astronauts are reunited inside the habitat, helmets off, smiles wide. They embrace one another in celebration. There is fatigue in their eyes, but also a gleam of triumph. For a moment, they allow themselves to revel in it. They have arrived on Mars and established a livable outpost, But duty never sleeps. There is much to do to secure this foothold. They set immediately to work on the habitat commissioning checklist that Mission Control has prepared. The crew spreads out through the single large compartment of the habitat, which has 2 levels, an open loft-like design connected by a short ladder. They systematically verify each subsystem now that it's under crew management. The environmental control panel is checked. Scrubbers are cycling CO2 properly, oxygen generators and circulation fans all operative. Water recycling units, which had been idle, are activated and tested with a small amount of water. They confirm the reactor is indeed supplying power steadily, voltage and frequency stable, and that the switchover from solar panels to reactor for primary power occurred without a hitch. They test communications from the habitat's own antenna system, pinging the relay satellite and confirming a solid link back to Earth. They even flip on a camera mounted outside the habitat to get a live view of the surrounding terrain and their lander in the distance, now shrouded in a settling cloud of dust. The image comes through on a wall monitor, and one astronaut murmurs, "What a sight." Throughout these checkouts, they remain methodical. They've rehearsed all of this in simulations on Earth. Still, doing it here, for real, carries extra weight. They announce each step, cross-check each other's work, and log the results. Mission Control listens in, though the conversation is one way due to the several-minute communication lag. Any response from Earth to a status report arrives long after the crew has moved to the next task. Essentially, the team must act autonomously, following protocols, but making on-the-spot decisions. It's something they trained extensively for, and now it's playing out flawlessly. They also take time to establish safety protocols in their new home. They locate and inspect the emergency medical kit, making sure the defibrillator and emergency oxygen masks inside are in working order. They review fire safety. The habitat has a fire suppression system, but they double-check the locations of handheld extinguishers and verify the smoke detectors and alarms by doing a quick test chirp. The sudden sound startles them in the otherwise quiet dome. They confirm that at any sign of a major issue, like a pressure leak, they can seal the airlock and retreat to the lander, which remains a backup safe haven. One crew member even walks the short distance back to the lander to ensure its cabin is still pressurized and systems on standby, then returns to the habitat, a quick excursion just to verify that redundancy. Dust mitigation is another important protocol. Martian dust is fine and clingy and contains toxic perchlorate chemicals that the crew does not want inside their living quarters. In anticipation, the habitat's entryway is designed as a mudroom of sorts. It has an inner lining meant to trap dust and a small vacuum system at the airlock. The crew puts this to use now. They spend a good half hour cleaning the airlock and their suits. Using brushes and electrically charged mats, they remove as much dust as possible from suit surfaces and boots. They had attached their exterior boots to the suit port outside. In one configuration, astronauts can leave their outer boots and suits attached to the exterior of the habitat to avoid bringing any dirt in, a feature of this habitat design. Indeed, 2 suits now hang on the outside wall of the habitat, latched onto suit port docks, like empty suits of armor waiting to be worn again. This means the crew entered through a sort of rear hatch of their suits, directly into the habitat, a clever approach that drastically reduced the amount of dust that got inside. The crew notices that only a fine film of reddish powder made it in, easily wiped up with a damp cloth. The habitat's filters will capture any remaining particles floating about. In short, the no dust inside protocol is working well. They all feel the gritty coating on their suit gloves and tools, but inside the habitat, they can run a finger along a surface and it comes up clean. Keeping their living environment as free of Mars dirt as possible will be an ongoing battle, but it is one they are well prepared to fight. By late afternoon, local Mars time, the habitat is fully commissioned. All lights are green. The crew takes a collective step back and marvels at the fact that their new home is not just surviving, but thriving. Warm air circulates, the hum of systems is steady and comforting, and the radiation storm shelter, a closet lined with extra water containers, is ready should they ever need it. They've even unpacked a few personal items. One astronaut has stuck family photos and a mission patch to a bulletin board above his sleeping berth, and another has set a small plush toy, a mascot, floating near the ceiling as a good luck charm. These small touches make the sterile module feel more habitable. There is still work to do before they can truly rest. They plan to retrieve more equipment from the lander while daylight lasts, ferrying over scientific instruments and additional food supplies. But they pause these tasks for a moment to address something very important: communication with Earth. The world has been waiting to hear from them. Using the habitat's stronger communication array, the crew records a brief video message intended for broadcast. They stand side by side in the frame, habitat walls around them, all in their casual flight suits now, no helmets. The commander speaks first. "Mission Control, this is the Ares crew. Reporting from Mars." A smile breaks across his face as he says it. There are whoops of joy from his crewmates. He continues, giving a concise summary. The landing was successful, the habitat is operational and secure, and the crew is safe and in good health. Each member then gives a short hello. They've agreed to keep it short and not too emotional, but each conveys their awe and gratitude. "The view is amazing," one says. "I can't wait to share everything we're seeing with you all." They know it will be anywhere from 10 to 20 minutes before Earth even receives this message, depending on the exact distance at the moment. But they also know millions of eyes will eventually see their smiling faces and rejoice. It's a strange feeling, speaking to a future audience across the void. But it reinforces how this moment isn't theirs alone. It belongs to everyone supporting and watching back home. Before signing off, they also perform a quiet ceremony. The pilot gently unfurls a rolled flag. It's the flag of their home nation, and alongside it the flag of Earth, a symbolic flag representing all humankind. In the low gravity, the flags don't hang the same as on Earth. They tend to float and drift. So they've mounted them on a wall behind the habitat's central table. The crew stands at attention and takes a photo for the history books. Humans in a habitat on Mars, flanked by the symbols of the societies that sent them. It's a brief, solemn moment. They know that later on they will plant flags outside too, perhaps during a live broadcast, but right now, the simplicity of pinning them to the habitat wall feels fitting, claiming this shelter for humanity peacefully and proudly. With official duties done, attention returns to practical matters. The astronauts share a quick meal, their first inside the habitat. They rehydrate and warm some ration packs, a stew of lentils and vegetables for some, a savoury meat dish for others. Sitting around their small fold-out table, on Mars, eating a hot meal, it feels almost unreal. There's laughter and chatter. They toast, with packets of fruit juice, to a successful landing and to the robot team that got everything ready for them. Looking out one of the habitat windows, they can see the light beginning to fade. The sun is dipping toward the horizon, casting long shadows from the habitat and lander across the ground. The Martian sky goes from dusty pink to a deepening amber. Sunset on their first sol has arrived. Even though adrenaline still courses through them, the long day and the heavy work of landing and setup have tired the crew. It's time to establish their first night's routine on Mars. They decide to implement a watch schedule for this first night, as a precaution. While all systems are running smoothly, they want someone alert in case an alarm or unexpected event occurs. They agree that two will sleep while one person stays up for a 2-hour watch. Then they'll rotate so everyone gets a decent rest. In later nights, if all goes well, they may not need a constant watch, but for now, it helps everyone's peace of mind. The habitat has 4 sleeping berths, essentially padded bunks mounted along one wall, each enclosed by a curtain. As the crew sets up these sleeping areas, they note with some glee that in Mars's gravity, things stay put. On the ship, they had to strap themselves into sleeping bags to keep from drifting. Here, they can lie down on a mattress and feel the gentle pull that keeps them in place. The simple act of stretching out horizontally is a pleasure beyond words. They unroll light sleeping bags and blankets, brought for warmth and comfort, since nights can get cold. One astronaut, preparing for first sleep, remarks that even the pillow feels heavy compared to what she's used to. A reminder of the gravity here. They each change into comfortable clothes, soft shirts and sweatpants, like a pajama of sorts, enjoying the freedom to be out of a pressure suit. Before lights out, the crew member taking the first watch goes through a final evening status checklist. He verifies that all entry hatches are sealed and locked. He does a quick scan of the habitat's atmospheric readings, all normal. He checks that the spacesuit batteries are on charge for tomorrow and that their rover's systems, still parked outside, are in standby. Satisfied, he dims the habitat's main lights, leaving just a gentle illumination akin to nightlights. The other 3 crewmates settle into their bunks. Each finds it hard to stop stealing glances out of the small viewport near the ceiling. Through that window, Mars's 2 tiny moons are visible tonight. Phobos, the larger moon, is hurrying across the twilight sky, a faint grey potato-shaped object moving noticeably fast. It orbits Mars in just about 7.5 hours, so it will zip overhead and set in a few more hours. Deimos, the smaller moon, is a tiny speck higher up, more stately in its slower orbit. The stars beyond are coming out in force as the sky dims to a deep blue, then black. The crew knows Earth is one of those stars now. Somewhere out there, a bright pinpoint that is their home. The thought is both solemn and soothing. Snug in their habitat, the astronauts lie in their bunks listening to the soft background hum of the ventilation system. The air inside is pleasantly warm, around 21 degrees Celsius, while outside the temperature has plummeted as night fully falls, down to minus 70 degrees Celsius and still dropping. They are thankful for the insulation and heater that keep this bubble of life cozy against the Martian cold. The first watcher pours himself a cup of rehydrated coffee, intending to stay gently alert while his companions sleep. He takes a seat by a port window, looking out occasionally at the subtle landscape under the moon's faint light. He can see the silhouette of their lander off in the distance, and the glint of starlight on one of the rover's solar panels. All is quiet and still. In their bunks, one by one, the other crew members drift off to sleep. It has been an extraordinary day, perhaps the most extraordinary any human has ever experienced, and now their bodies demand rest. Each astronaut feels a mixture of profound relief, excitement for the future, and a gentle homesickness as they finally close their eyes. They are completely safe in their sturdy little habitat, and that knowledge allows them to surrender to fatigue. The first night on Mars passes peacefully. The habitat systems quietly run through the dark hours, keeping the air fresh and the temperature even. The sleeping astronauts dream, who knows of what, of Earth, of loved ones, or perhaps of the barren beauty just outside their walls. The crew member on watch writes a few lines in the mission log and notes that outside, the winds are calm and the stars incredibly bright. At one point, he steps into the airlock and through its small window gazes up at the sky to see Earth. Indeed, there it is, a modest bluish evening star low on the horizon. He raises an arm in an instinctive wave, though no one is there to see it. As the night deepens, Phobos sets and rises again. It will do so twice before dawn. The familiar constellations slowly wheel overhead, though shifted in the sky from the view on Earth. Time seems to slow inside the habitat. The watchstander fights off his own drowsiness, not from boredom, but from the cumulative exhaustion of the day. Eventually, he gently wakes the next person for their turn at watch. Quietly, they trade places, and he slips into his bunk, falling asleep almost instantly. And so, under the pale light of an alien sky, with their electronic hearth keeping them warm and alive, the first humans on Mars end their first day. It is the beginning of a new chapter in human history. In the coming days, they will venture out, explore, build, and learn to truly live on this world. But tonight, within their dome of light, amid the endless Martian dark, they simply rest. 5 explorers, counting the ever-vigilant robotic helpers, outside alone on a planet, together. The gentle hiss of the habitat's air circulators and the soft snoring of a contentedly sleeping crew are the only sounds on this quiet Martian night. Tomorrow, when the pale dawn breaks over the dusty plains, a new day will begin. A day where humanity is firmly present on Mars, ready to continue the great adventure that this first night has so serenely inaugurated. In the dawn light of Mars, a small team of explorers gazes across the vast, reddish expanse, searching for the perfect place to call home. The landscape offers a silent panorama of possibilities. Open plains stretch out under a peach-tinted sky. Ancient craters pockmark the horizon with their deep shadows. And not far off, a dark opening yawns in the ground where a collapsed lava tube beckons. Here, on these alien sands, they must choose their ground. The decision is not just about geography, but survival. Every option, a flat plain, a crater basin, or a cave-like lava tube, holds both promise and peril, and the settlers weigh them in thoughtful silence. A broad and level plain offers simplicity and sunlight. On the open flatlands, it is easier to land their spacecraft and deploy equipment without the danger of jagged terrain. Nothing obstructs the sun's rays here, a crucial advantage on a planet where warmth and power are scarce luxuries. At midday, the sun hangs in a butterscotch sky, bathing the plains in light that is bright yet gentler than on Earth. This far from our home world, Mars receives less than half the solar energy we know back on Earth, but on a clear day, the plains still glow rust-orange beneath the sunlit sky. The explorers imagine rows of solar panels here, soaking up those rays to fuel their nascent colony. They picture habitats and greenhouses laid out with ample space to grow. Yet, the openness that promises sunshine also brings exposure. With no natural walls, the plain offers little protection from radiation above or from the harsh winds that occasionally sweep across the Martian deserts. The team knows that on Mars, the atmosphere is thin to the point of near non-existence, and even a roaring wind carries only a feeble push. A 100-kilometer-per-hour dust storm on Mars feels like little more than a light breeze back on Earth. But those winds can still blanket the world in dust. On an unshielded plain, a colony would face cosmic rays from space and the full brunt of dust storms dimming the sky. The settlers feel both drawn and wary, recognizing that a simple, sunlit plain will demand that they create all their own protection from scratch. They turn their eyes to a grand impact crater nearby, its rim rising like a natural fortress. Settling in a crater could offer a partial embrace from Mars itself. The crater's ancient walls, carved by a long-ago meteor impact, could act as barriers against the gusting winds and maybe even block some radiation coming at low angles. Down on the crater floor, the air pressure is marginally higher than the surrounding highlands, only a few percent more. But on Mars, every bit counts. Low elevation means a thicker layer of atmosphere above, providing slightly more cushion during landing and a touch more shielding from cosmic rays. Standing at the edge, the explorers can almost imagine the crater as a colossal bowl collecting what little air and warmth Mars possesses. In fact, this region sits in the northern mid-latitudes, a literal middle ground between the water-rich poles and the sun-soaked equator. Here they hope for a balance. Perhaps buried ice lies underfoot, and the sun still climbs high enough in the sky to sustain solar power. The crater floor, blanketed in dust and rock, holds hints of hidden water. In one spot along the rim, a recent meteorite strike has freshly excavated the soil, revealing a telltale glint of bright frost. The sight is astonishing. A patch of pure ice peeking out from just beneath the surface, catching the morning light with a faint blue sparkle. It is as if Mars itself is offering up a clue. Beneath its red veneer, there is water waiting to be tapped. The explorers share a silent nod. A crater site could give them both protection and precious resources. But the crater has its challenges too. Its slopes are treacherous in places, and hauling equipment in and out would test their ingenuity. The bowl that shelters could also trap cold air at night, turning the crater floor into a frost pocket under the stars. Still, the allure of that exposed ice and the partial sanctuary of those high rocky walls makes the crater a strong contender in their minds. Perhaps most intriguing is the dark cavern that lies not far from their landing spot, a window into the subsurface world of Mars. A gaping round hole in the ground marks where a segment of an ancient lava tube has collapsed, revealing a tunnel that extends into shadow. The explorers carefully approach the opening as the morning sun angles in, illuminating just a few meters of the interior before darkness swallows their view. This could be a doorway to a ready-made base, created eons ago by volcanic fires. Within such a tube, thick rock overhead could shield a habitat from cosmic radiation and micrometeorites naturally. The temperature inside might be more stable than the wild swings of day and night on the surface. Standing at the threshold, they feel a cool stillness emanating from below. It's quiet, profoundly quiet, as if sound itself is hesitant to venture out from the cave. One explorer kicks a pebble and watches as it skips into the blackness, the clatter of stone on stone echoing from the hidden depths. A lava tube could be a sanctuary. It's often been said by visionaries that future Martians might live in such caves to escape the radiation and extreme climate. Here, Mars offers a roof already built, a protective cocoon beneath the surface. The idea of placing their homes under arches of basaltic rock, safe from solar storms and cosmic rays, is tantalizing. In their imaginations, they trace where walls, doors, and lights might go in that subterranean space. How comforting it would be to inhabit a natural vault, where the awful emptiness of the Martian sky is replaced by solid shelter. Yet mysteries linger in the darkness. They do not know how far the tube runs, or what its structural integrity is after untold years. There may be jagged terrain inside, unseen drops, or even deposits of ice or gases. The prospect of venturing into that unknown, to explore and perhaps domesticate it, sends a thrill down their spines. It feels a bit ominous too, like entering the lair of the planet itself. One explorer remarks softly that if humans were to find life on Mars, maybe some hardy microbes hanging on, caves like this might be where they'd hide. The thought makes the lava tube feel both inviting and enigmatic, a place for discovery as much as refuge. The team convenes back at their rover, their boots crunching in the red dust, to discuss what they've seen. They speak in low, calm voices, aware that this decision will shape the fate of their colony. In the thin air of Mars, their words carry an almost eerie clarity through the intercoms of their suits. They weigh the options: the open plain with maximum sunlight and simplicity, the crater with its promise of ice and partial shelter, and the lava tube offering unparalleled protection and the intrigue of the underground. Slowly, a consensus emerges. They will begin their outpost on the flat plain near the entrance of the lava tube, right at the foot of the crater's outer rim. It is a choice born of compromise and foresight. On the plain, they have room to land and build with ease, and abundant sunshine for power. By situating themselves adjacent to the crater and cave, they keep within reach of natural shelters and known ice deposits. The site is a gentle slope leading into the crater valley, a place where they can imagine constructing tunnels or roads into the crater floor over time. For now, it offers a relatively flat, stable foundation for their first habitat modules. Beneath their feet is soil that their instruments confirm holds hydrogen signatures, likely a mix of bound water and ice grains locked in the dirt just a meter or two down. The proximity of the lava tube means if radiation levels spike during a solar flare, they could temporarily take cover under rock. And in the long term, they might even expand the base into the cavern itself, using it as a vast subterranean warehouse or farm shielded from cosmic rays. Standing together at this chosen ground, the pioneers feel a wave of relief and determination. The hardest part of any journey is often the first step, and now they have taken it. They have a place to begin. High above, the pale disk of the sun climbs higher, as if heralding the start of a new chapter on this alien world. The site is decided. Now the ground must be transformed into a home. With the location settled, the astronauts turn to the immense task of carving out shelter on this unforgiving terrain. Mars will not coddle its new visitors. If they want safety, they will have to build it themselves. Under the mid-morning sun, they begin deploying the tools and machines that will fashion their first habitat. The land here is silent, but for the faint whir of electric motors and the crunch of boots in regolith. The air is too thin to carry sound far, so their work seems almost dreamlike, as if happening in a hush. Yet there is nothing gentle about the environment they must tame. They start by unloading an inflatable habitat module, a sturdy shell that, once filled with air, will swell into a dome-like living quarters. This module, shipped from Earth tightly packed, is to be their initial haven against the elements. The crew finds a level spot and clears the loose rocks, preparing a foundation. With methodical precision, they activate small gas canisters to inflate the habitat. The structure rises slowly, its walls made of multiple layers of tough polymer and fibre, strong enough to hold an atmosphere inside. As it unfolds, it reminds one of the explorers of a giant translucent cocoon unfurling in slow motion. In a matter of hours, what was once a bundle no larger than a car now stands as a bulbous dome on the Martian plain, the first true home on Mars, albeit a fragile one. Fragile, because a simple pressurized dome on the surface is only a beginning. The explorers know that Mars is drenched in high-energy radiation from the sun and beyond. Without Earth's magnetic field or thick atmosphere, cosmic rays and solar particles rain down unhindered. Inside that dome, the crew would be safe from the vacuum and cold, but not from the invisible danger of radiation that can damage their bodies over time. They need to fortify their shelter, and the answer lies all around them in the ruddy soil of Mars. The dome must not remain exposed. It needs a thick blanket, a protective shield of Martian regolith. And so the next phase of construction begins, covering and reinforcing the habitat with the very ground it sits on. In the thin sunlight, autonomous robots spring to life to assist the crew. One is a squat, treaded machine with a flat scoop, essentially a small bulldozer designed for extraterrestrial work. It starts ploughing the loose topsoil, pushing it toward the habitat's base. Others are spider-like robotic arms mounted on mobile platforms, carrying nozzles and strange swiveling heads. These are the 3D printing robots, the builders that will sculpt a more permanent refuge. As the bulldozer bot piles mounds of soil against the lower walls of the dome, the 3D printing units position themselves around the perimeter. Under teleoperated guidance and pre-programmed patterns, they begin to extrude a thick paste made from Martian soil mixed with a binder. Earlier, the crew prepared this mixture, using some of their precious water supply to moisten the fine regolith and a pinch of chemical hardener they brought from Earth. The first printer robot hums, and a nozzle begins to spit out the paste, a dark, mud-like ribbon of Martian concrete. In steady, sweeping motions, the robot lays down the material around the base of the dome, tracing a circular foundation. Another robot follows, adding the next layer once the first has set enough. They are implementing a technique known as contour crafting, in which molten regolith and a binding agent are extruded from a nozzle to create infrastructure layer by layer. This process can be used to autonomously build monolithic structures like radiation shielding and rocket landing pads. In real time, the crew watches as their habitat gains a shell. Inch by inch, a solid wall is rising around the inflated dome, like a protective cocoon of adobe. Over several days, the robots methodically build this shield taller and thicker, leaving openings where airlocks and future windows will be. The structure they create is not one solid lump, but an engineered hollow shell, perhaps with a honeycomb or foam-like internal pattern to save material but maintain strength. When finished, it will be a kind of bunker encasing the dome, able to stop deadly radiation and also buffer against the drastic temperature swings of Martian day and night. While the printers work, the crew continues to tend to many tasks by hand and remote control. They deploy a lightweight crane to hoist up prefabricated support arches, placing them over the dome to help bear the weight of the coming regolith blanket. Each arch, made of a high-strength alloy, anchors into the ground at both ends, forming ribs over the habitat. Once these are in place, the crew directs the bulldozer to start dumping more soil onto the dome's top. Carefully, layer by layer, the dome is buried until its once whitish surface is mostly obscured by a mound of brown-red dust and sand. By the end, more than a meter of compacted Martian soil covers the living quarters, enough to reduce radiation exposure to much safer levels for long-term habitation. Standing back, the explorers admire the result of these efforts. Their first Mars home now looks like a low hill on the landscape, indistinguishable from natural terrain, except for the metal hatch of an airlock protruding, and a few sensor stakes and communications antennas poking out. They know from studies that a layer of Martian soil, about a meter or more thick, can cut radiation exposure significantly, protecting them from most solar flares, and even much of the constant cosmic rays that a thinner shield would let through. What they have built is an Earth within Mars, a pocket where Earth-like conditions can exist, shielded by Mars's own rocks and soil. The new regolith shield not only guards against radiation, it also will help regulate temperature. Mars is a world of extremes. Scorching sunlight can heat surfaces during the day, but at night, with such a thin atmosphere, heat radiates away into space, and the cold comes biting. Inside their buried dome, the crew will be buffered from those swings. The soil acts as insulation, keeping the interior from freezing at night and overheating in daytime. In this way, the Martian ground itself becomes their ally, a guardian wrapping them in a more stable microclimate. The irony isn't lost on them. They left Earth to live on Mars, and now a piece of Mars will always be living around them in the form of these protective walls. As the habitat fortification proceeds, the crew also sets out to construct other vital structures around their base. Using the same in situ construction approach, they plan to build up walls for workshops, storage sheds, and protective berms. One immediate concern is their landing zone. When their vehicle descended onto Mars, its powerful engines scorched and blasted the ground, sending dust and grit flying. They know future landings should be safer and cleaner. Therefore, they select a nearby flat patch and direct the robots to start creating a proper landing pad. Again, the printers pour out regolith concrete, this time in broad, flat rectangles. They print interlocking tiles and then fuse them with blasts of heat, perhaps using a focused solar reflector or microwave energy to sinter the regolith until it becomes a hard, stone-like slab. Slowly, a mosaic begins to cover the ruddy ground, forming a circular pad wide enough to support incoming spacecraft. It's a new experience, watching construction happen almost autonomously on another world. In one sense, it's primitive, dirt and rock being shaped into simple forms. But it's also groundbreaking, demonstrating that they truly can build a settlement using local materials. The settlers recall the studies done back on Earth. NASA and other agencies had proven in labs that regolith could be melted and solidified into bricks, beams, and pad surfaces. Now they see it unfolding in reality under the Martian sun. This landing pad, once complete, will prevent the next ship from gouging the terrain or spraying debris into their precious habitat. It's a mundane piece of infrastructure, perhaps, but absolutely crucial for a sustainable outpost. Day by day, the base camp transforms. The habitat is sheltered and pressurized. The landing pad is taking shape. Excavations for an underground trench to lay cables and pipes are dug, then covered. The initial work is hard and often tedious, but it carries a reassuring rhythm. Each sunset, the crew returns to their snug, half-buried dome, and each sunrise they venture out again or send their tireless robots to continue the labor. Over time, a casual observer might not even recognize that this hillside and cleared area is the beginning of a human colony. It could appear like just another part of Mars, until one spots the geometric pattern of the landing pad or the glint of solar arrays being erected. The subtlety is intentional. The pioneers are learning to work with Mars, blending their structures with the landscape to gain strength and cover. At last, with the main habitat secured and basic infrastructure in place, the immediate frenzy of construction can ease. As the dust of digging and printing literally settles, the focus shifts to the lifeblood of the colony: resources. The settlers have a roof over their heads now, but a home is more than walls. They need water to drink and grow food, air to breathe, and power to keep it all running. Mars has offered them protection. Now it is time to see if it will yield the materials of life. The next challenge looms: to find and extract water in this arid world, turning ice into liquid sustenance. And so, without fanfare, the crew moves on to the next phase of their mission, prospecting for the water that will transform their shelter into a living oasis. Water is life, and on Mars, water is also hope. Though the land around them looks dry as bone, the explorers know that hidden beneath the dusty surface, the red planet still clings to significant quantities of water, mostly in the form of ice. Armed with orbital maps and ground-penetrating radar, the team sets out to locate a reliable source of this buried treasure. Not far from their base, beyond a scatter of boulders left by ancient floods, their instruments pick up a strong indication of hydrogen just below ground. Perhaps it is a lens of nearly pure ice or a layer of permafrost, soil loaded with frozen water. The crew decides to investigate up close. They dispatch a rover equipped with a drill and a spectrometer to sample the site. On the rover's live camera feed, they watch as the drill bores a small hole into the ochre soil. A few tens of centimeters down, it suddenly bites into something different. The resistance lessens, and the drill spins freely, as if in softer material. Then a telltale sign. White clumps begin appearing in the drill flutes. It's ice, finely shattered by the drilling. The rover's scoop brings up a sample into the sunlight, and as they observe via remote microscope, they see it. Tiny ice grains glistening among the dirt, sublimating slowly in the thin air. A cheer rises in the habitat. Even though the presence of water was expected, there is an emotional surge in confirming it personally. In this moment, the boundless dry loneliness of Mars feels a little less hostile. Water exists here, within reach. Immediately, plans swing into action to extract this water in usable form. There are several methods at their disposal, some tested on Earth, some only theorized. Since the ice lies just a meter or two down, one straightforward approach is to dig it out. The crew sends an excavation robot, essentially a powered auger, to drill a wider bore. As it grinds its way into the frost layer, they add gentle heat via embedded heating coils. Slowly, a narrow well begins to form, not by removing all the ice, but by melting it in place. This approach, called a Rodriguez well, or Rodwell, is borrowed from practices in Earth's Antarctic outposts. The concept is elegant. By creating a cavity in the ice and keeping it warmed just enough, a pool of liquid water can collect at the bottom, which can then be pumped out of the well for use. The explorers carefully monitor the energy input to avoid the water freezing solid or boiling away. After many hours, sensors indicate a small pocket of liquid water has accumulated in the borehole. With measured optimism, they activate a submersible pump lowered into the hole. There is a brief delay, and then, inside the habitat, a storage tank begins to fill with the first trickle of Martian water. Actual liquid water, drawn from the ground of Mars, starts flowing through their pipes. It is a moment both ordinary and profound. The water itself looks like any other, clear, with perhaps a faint sediment of red dust. But this water has not seen liquid form for perhaps millions of years until now. In a very real way, the colonists have just revived part of Mars's ancient hydrology to serve human needs. They collect a few litres initially, mindful of not overtaxing their nascent well. This sample is brought into the habitat's lab, where the crew tests its purity. As expected, the melted ice contains some dissolved minerals and perchlorates, those reactive salts common in Martian soil. Nothing insurmountable. Their life support systems include filters and resins ready to remove these contaminants. Through filters, distillers, and chemical treatments, they purify the water until it meets the standards for drinking and crop use. Soon enough, one of the astronauts lifts a sealed bag with a small amount of this water, now clean. In a small ceremony of sorts, they each take a sip. It's flat, a little metallic perhaps from the traces of iron, but it's water, cold and wet and real. They grin at each other. It is as if Mars has given them a welcome gift at last. Extracting water from the ice is one part of the challenge. The team knows they will need a continuous supply, and likely far more than what a single borehole can provide over time. So, they also experiment with another method for more distributed ice or hydrated minerals. Using the soil gathered by the rover's scoop, they place it into a heated oven-like device in the lab. They raise the temperature and watch steam begin to condense on a cool plate as the soil releases its moisture. In the future, they can scale this process up. A small processing unit could bake shovelfuls of regolith in sequence, capturing water vapor and condensing it. Techniques like these, auger dryers, and even microwave ovens that could free water from soil were developed through years of research for exactly this purpose. It's gratifying to see them actually working on Mars. Though energy intensive, baking soil for water could allow them to harvest moisture even from dirt that's only mildly damp. Every drop will count if they aim to grow their colony. Now that they have raw water, the settlers turn it into all the forms needed for a self-sustaining life. They fill drinking water reserves and hook the supply into their life support system's recycling loop. A portion of the water is directed to an electrolysis unit, a machine that splits water molecules into oxygen and hydrogen using electricity. This is a tried and true technology. On the International Space Station, electrolysis provides much of the breathable oxygen for astronauts. Here on Mars, the oxygen gas produced is siphoned off and pumped into storage tanks to top up the habitat's atmosphere as needed. The hydrogen byproduct is not wasted either. Some of it may be combined with Martian atmospheric carbon dioxide in a chemical reactor to create methane fuel, a process that could one day fill the tanks of rockets bound back to Earth or powering ground vehicles. Indeed, water is the keystone resource. From it, they can make air, fuel, and of course sustain plant life. The crew also installs a device resembling a small golden cube, a cousin of an experiment that flew on the Perseverance rover. This is an updated MOXIE unit, Mars Oxygen In Situ Resource Utilization Experiment, designed to draw in the thin Martian atmosphere and strip oxygen from the abundant carbon dioxide. With a soft hiss, the machine begins intaking the outside CO2 and electrochemically snapping the molecules, releasing oxygen. This oxygen too flows into their storage, while the carbon monoxide waste is vented back out. It's a slow process, yielding only grams of oxygen per hour, but it operates continuously, augmenting their supplies. With the MOXIE running and the water electrolyzer humming, the habitat's internal tanks gradually accumulate a surplus of oxygen. There is no more precious safety net than this invisible stockpile. It means that even if an infrequent supply shipment is delayed, or an emergency forces them to seal themselves inside for a time, they will not suffocate. Inside the habitat, the crew begins setting up a complete water recycling assembly. They know that the easiest water to obtain is the water you don't lose in the first place. Every drop of water that leaves their bodies as sweat, breath, or urine is captured by the life support systems. Exhaled air is run through condensers so that moisture from their breath collects and drips into reclaim tanks. A filtration unit handles urine, employing advanced membranes and chemicals to remove impurities and produce clean, potable water. Nothing goes to waste. They achieve a closed loop where about 90% or more of all water is recycled, much like on the space station. The crew sometimes jokes darkly among themselves in the evenings, the old line that yesterday's coffee becomes tomorrow's coffee. But they take comfort in the fact that this technology works reliably. Their survival on Mars is a dance of constant reuse and renewal. With water and oxygen now steadily flowing from Martian sources and recycling efforts, the base is becoming more self-sufficient. The dusty tanks and pipes that snake through their outpost carry the lifeblood of the colony. Outside, the sun climbs toward noon, and a thin, wispy cloud, a rarity on Mars, passes overhead as if observing the humans' determined efforts. The next imperative for the crew is to ensure their living environment remains not just supplied, but truly livable. Water and oxygen alone do not make a home. The air around them must be kept at the right pressure and temperature, a bubble of Earth-like climate amid Mars's frozen desolation. As they move on to address these needs, the crew reflects that they are, in essence, bottling up little pieces of Earth, the air, the warmth, the water, and sustaining them here on Mars through ingenuity and relentless work. Each system they bring online is another thread tying them to survival. Now it is time to weave those threads into a stable habitat where they can breathe easy and stay warm even as the Martian night falls. Inside the habitat, a new world exists, a pocket of breathable air, warm and moist compared to the dry, chill outside. Creating and maintaining this Earth-like bubble is one of the colony's highest priorities. After all, the settlers can survive only seconds in the raw Martian atmosphere without protection, but inside their habitat, they remove their helmets and live in shirt-sleeve comfort. Achieving that comfort is a triumph of engineering. The habitat's interior is now pressurized to a safe level, though not as high as Earth's sea-level atmosphere. The crew and mission planners chose a compromise pressure, high enough to breathe easily, but lower than Earth standard to reduce strain on the habitat structure and conserve resources. At around perhaps half an atmosphere, the internal air still feels normal to the crew after a brief adaptation. Like living at a high mountain altitude, this reduction in pressure drastically lessens the force trying to push the habitat walls outward. Were they to fill the habitat with full Earth sea level pressure, each square meter of the structure would have to withstand roughly 10 tons of force pressing from inside, a crushing load that would demand far heavier construction. By using a lower pressure, with an oxygen-enriched mix, they avoid that extreme strain, while still providing each person the oxygen they need for their blood. The habitat's composite shell and its added regolith shielding easily handle the current pressure, and the crew moves about inside without the encumbrance of spacesuits, breathing freely the air they have made. That air is a careful blend of gases. The primary component is nitrogen, an inert gas that serves as the bulk filler, just as it does in Earth's atmosphere. Mars's atmosphere, tenuous as it is, contains a small amount of nitrogen and argon, and the crew has been working to isolate those gases. Using compressors and adsorption filters, they pull in Martian air from outside and concentrate the nitrogen and argon, which are then introduced into the habitat to build up the pressure without adding too much oxygen. They know the danger of an overly oxygen-rich environment. The risk of fire would spike if the habitat were filled with pure O2. So they keep oxygen at roughly the same partial pressure as at sea level on Earth, around 21 kilopascals, and let nitrogen, along with a bit of argon, make up the rest. Some of this nitrogen came compressed in tanks from Earth, an initial supply for exactly this purpose. The rest is slowly accumulated from the Martian sky. Argon, which is also abundant in Mars's CO2-heavy atmosphere, serves as a useful buffer gas as well, and the crew might use more argon in the mix if nitrogen supplies run low. Within the habitat, the environment is kept remarkably Earth-like. The temperature is maintained around a comfortable 20 degrees Celsius during the day, a pleasant shirt-sleeve climate that almost lets the crew forget the lethal cold just beyond their walls. At night, when external temperatures might plummet far below freezing, the habitat systems kick in more heating to ensure the living quarters only dip a little in temperature for sleeping comfort. Heating is provided in part by electrical heaters and in part by clever use of waste heat from other systems. The life support machines, the pumps, the electronics, all give off heat when running. Instead of letting that warmth dissipate uselessly, The habitat is designed with heat exchangers that capture it and circulate it through the living space, or store it in thermal masses in the floor for slow release. Likewise, the water brought up from underground, initially near 0 degrees Celsius, is run through heat exchange coils that warm it before use, so it doesn't chill the habitat's interior. In the daily cycle, the greenhouse, soon to be full of plants, may also contribute warmth and humidity by day, which then must be balanced with dehumidifiers and radiators by night. It's a continuous balancing act. Too cold, and they risk pipes freezing or the crew suffering. Too hot, and equipment might overheat, or condensation could form in unwanted places. Humidity is another factor they manage closely. With people living and soon plants growing, water vapor fills the air from every breath and transpiring leaf. Too much moisture could condense on cold surfaces and cause problems like mold or corrosion. Too little could dry out throats and increase fire risk. So they maintain a comfortable middle ground, often around 30 to 50% relative humidity. Dehumidifiers capture excess water from the air and feed it right back into the water supply, while humidifiers can add a bit if things get too dry. The crew finds that the presence of a normal-feeling humidity makes a big difference to their comfort. It prevents nosebleeds and dry skin, making this sealed dome feel more like home and less like a lab. Crucial to survival is the constant scrubbing of carbon dioxide from their indoor air. Each person exhales CO2 with every breath, and in an enclosed environment, it doesn't just waft away. They have installed chemical scrubbers that use materials like zeolite or lithium hydroxide to trap CO2, mirroring the technology long used in spacecraft and submarines. The trapped CO2 is then periodically released in concentrated form and either vented outside or, better yet, fed to the greenhouse plants as a nutrient. In fact, as the greenhouse becomes operational, the crew will route some of the habitat's ventilation through the plant chambers, allowing the flora to feast on the CO2 humans produce. And in return, those green leaves will give off oxygen. This symbiosis of crew and plants is at the heart of creating a regenerative life support loop, and already the crew can see it starting. A small field of sprouts in the greenhouse module that indeed are thriving on what the humans breathe out. All of these atmosphere control systems are monitored by a central computer that alerts the crew to any imbalance. If pressure drops suddenly, say due to a small puncture or leak, alarms will sound and reserve oxygen can flood the cabin while the leak is sealed by automatic valves. The habitat is compartmentalized as well, divided by bulkhead doors so that a breach in one section can be isolated rather than venting the entire living space. The crew practices emergency drills, sealing sections and donning masks, preparing for an event they hope never happens. But they are keenly aware that their lives depend on maintaining this bubble of air. Mars's outside pressure is barely 0.6% of Earth's, essentially a vacuum, so even a fist-sized hole could lead to a dangerous loss of air in minutes. Redundancy and vigilance are their watchwords. They trust the engineering that went into this habitat, yet they also double-check seals and listen in quiet moments for any faint whistle of escaping air. Within their pressurized haven, the crew finds moments of genuine comfort. There is a psychological warmth to being able to remove one's helmet, to hear each other's voices directly and not through tinny speakers, to smell a hot meal or the faint metallic scent of the machinery, or eventually the green, living smell of plants. These small things ground them in their humanity. At night, Martian sols are about 39 minutes longer than Earth days, but they keep a roughly Earth-like daily schedule. When they dim the habitat lights and prepare for sleep, one of the astronauts often takes a moment to sit by the small, thick window that peers outside, Through that porthole, they can see the barren surface and the stars beyond, and it amazes them that just a few centimeters of glass separate their warm, breathable room from the lethal vacuum and cold outside. Sometimes a thin layer of frost forms on the outside of the window as the night cold meets the warmer air inside. It's a gentle reminder of the bitter environment lurking just beyond their cocoon. And yet, as the explorer rubs the frost with a gloved hand from inside, clearing a patch to gaze at the moons, Phobos and Deimos rising, there's a sense of peace. Inside these walls, they have created spring in the midst of an endless winter. They have air, they have warmth. Their shelter is truly a home now, filled with light and safety against the dark. Even as the habitat systems work to keep the environment coddled and Earth-like, the crew steps outside regularly and is instantly reminded of Mars's true nature. Each time they cycle through the airlock, donning suits and hearing the hiss as pressure equalizes with the near vacuum outside, they experience the alien cold anew. A few minutes of standing on the surface can chill an unheated tool to biting frigidness. Even though the sunlight may feel warm on a black suit, one side of their body could be warm while the shadowed side is extremely cold. But they have mastered living between these two worlds, one inside engineered by them, the other outside indifferent to their presence. Now, with a secure habitat and essential resources flowing, the colony can't run on life support alone. All these systems, water pumps, air scrubbers, heaters, lights, need energy. Power is the next critical component to sustain and expand this tiny foothold on Mars. Recognizing this, the team has from the start been deploying their power infrastructure. Around the habitat, the flat Martian ground begins to host a growing array of solar panels. One by one, they unfurl like black petals on the rust-colored soil, each oriented to catch the daily arc of the sun. These solar arrays are high efficiency, specially made for the Mars spectrum. In the thinner atmosphere, more ultraviolet light reaches the surface, and the panels are designed to handle that too. Still, Mars challenges them. At this distance from the sun, the light that arrives carries only about 43% of the intensity of sunlight at Earth's orbit, and the dusty sky further saps some of that strength before it reaches the panels. The crew knows from calculations that they will need a solar field covering a large area to generate the kilowatts required for a habitat. So they spare no effort in setting up panel after panel, connecting them in arrays with careful alignment. Over several sols, the solar farm grows until it sprawls over terrain, perhaps the size of a football field. In the peak of the afternoon, when the sun is highest, this field gleams and sends a bounty of electricity coursing into the base's microgrid. On days when the sky is clear and the sun shines strong, the power is ample. The colony hums with activity, machines charging, water being electrolyzed, perhaps energy-intensive experiments running. But the crew always has an eye on the horizon for the first sign of dust. Mars is infamous for its dust storms, which can arise with little warning from a distant gust and eventually roll over the landscape like tawny fog. One afternoon, a brownish haze appears in the west and slowly envelops the sun, tinting the sky from butterscotch to deep orange, and then to an unsettling brown-grey. The solar panel readouts show a steep drop in output as the sunlight weakens. In a matter of hours, it feels like twilight has come early. The explorers are not surprised. They knew this day would come. They quickly implement their dust storm protocols. Non-essential systems are powered down to conserve energy, and battery storage units kick in to supply critical loads. Through the dim light, the astronauts can barely make out their solar field now, just vague dark shapes in a rust-red gloom. The dust storm is not ferocious at ground level. The wind is gentle, merely brushing their suits as they step out to inspect things. Yet it's persistent and all-encompassing. The sunward sky becomes a featureless glow. For days, the storm persists, and the solar panels produce only a trickle of power, barely enough to charge a few devices. This is where the foresight of a diverse power supply pays off. Robots can hibernate when energy is lean, but humans cannot, so the base was designed with backups. In the habitat, a different source of power quietly takes the lead. Situated a safe distance from the main living quarters is a squat, robust unit about the size of a large trunk on stilts, with a small tower radiating heat. This is a compact fission reactor, a marvel of modern engineering known as a kilopower reactor. While the sun hides behind dust, the reactor steadily continues delivering energy, utterly unfazed by the changing weather or nightfall. Inside, a core of uranium fuel generates heat through fission, and passive sodium heat pipes transfer that heat to high-efficiency Stirling engines, which convert it to electricity. The reactor produces a constant output of about 10 kilowatts of electrical power, continuously for 10 years or more. For comparison, the average US household draws on the order of 5 kilowatts. The crew had activated this reactor soon after landing, once they were a safe distance away, and it has been their backbone power supply ever since. Now, during the storm, it proves its worth beyond doubt. Systems that had idled are switched back to normal. The batteries, which were beginning to drain, hold steady and even start recharging. Inside the habitat, lights remain on, heaters keep everyone warm, and life support never falters. The crew experiences the storm almost as a curious spectacle rather than an existential threat. Through a window, they watch the peculiar darkness and swirling dust, sipping warm drinks powered by the atom. The knowledge that their reactor is impervious to the sun's whims is deeply comforting. It means they can endure the weeks-long tempests that plunge solar output to nearly zero, without fear of freezing or suffocating. When the dust finally settles and the sun returns, the solar arrays cheerfully resume their share of the work. The colony's energy strategy is one of redundancy and balance. On a bright, clear sol, solar power might provide the bulk of electricity, while the reactor perhaps idles at a lower setting or is put into a maintenance mode. But at night or during storms, the reactor is the hero, carrying the colony through the dark. The presence of steady fission power also allows the colonists to think more ambitiously. They are not confined strictly to equatorial regions or constant sunlight. In fact, their chosen latitude, a bit north of the equator to be near water ice, is quite viable because of this reactor. With it, they could even consider expeditions to higher latitudes or polar outposts where sunlight is seasonal at best. Nuclear power has given them freedom on Mars, freeing them from total dependence on fair weather. One of the astronauts recalls a quote from back when this tech was in testing. A scientist said such reactors would be a game changer for Mars, enabling survival through long nights and dust storms and opening up the map for landing sites previously off limits. Living through this storm, the crew now appreciates the full truth of that statement. To store energy for shorter fluctuations, the colony relies on an array of batteries lined up in an insulated vault adjacent to the habitat. These battery banks, using advanced lithium-ion or perhaps newer solid-state cells, charge up when excess power is available and discharge when needed. They serve to buffer the microgrid, smoothing out transitions. For example, at sunset each evening, as solar production wanes, the batteries seamlessly pick up the slack before the reactor output is adjusted upward. This keeps the electricity supply constant, avoiding any flicker in the habitat's systems. The colonists have also brought several regenerative fuel cells, devices that can operate in two modes, using surplus power to break water into hydrogen and oxygen, which are stored, and then later combining those gases to generate electricity and water when needed. This chemical battery complements the solid-state batteries, adding another layer of resilience. On a sunny Sol, if their water extraction has provided plenty of H2O, they use some excess solar power to produce hydrogen and oxygen, effectively bottling sunshine in chemical form. Then, during a peak demand, or if both solar and nuclear were for some reason offline, those fuel cells can supply power for many hours, the hydrogen and oxygen recombining into water and electricity in a controlled reaction, much like what powered the Apollo spacecraft. The only difference is here they can recover the water and do it all over again, hence regenerative. The solar farm itself requires its own maintenance rituals. Even without storms, dust slowly accumulates on the panels, dulling their efficiency. But unlike the lone robotic rovers of the past that had to hope for dust devils to clean them, here human hands and their robotic helpers can intervene. Each morning that the weather is clear and winds are calm, one of the crew or a tele-operated droid takes on the role of cleaner. Often an astronaut in a suit will gently brush off the fine red powder with a soft tool, making careful strokes to avoid scratching the panel surfaces. Other times, they use a puff of compressed CO2 gas to blow away the dust. It turns out that one engineering problem is actually made easier by having humans on site. Dust accumulation on solar panels has a simple solution: a duster. A little routine sweeping keeps the arrays operating near peak efficiency, a task that vexed robots for decades, but is trivial when you have people around. The crew doesn't mind it. In fact, the morning wipe, as they call it, has become a pleasant routine for some, a chance to step outside in the brisk Martian dawn and watch the sun rise while performing a light chore. It's reminiscent of cleaning frost off a car windshield back on Earth, albeit in a far more exotic setting. Apart from solar and nuclear, the colonists ponder other potential power sources. Wind turbines stand stored in parts in the cargo, but they are small prototypes. They know Mars's thin air, and even its furious storms, carry far less energy than Earth's winds. Even the most violent dust storm, blowing at over 100 kilometers per hour, exerts aerodynamic force equivalent to little more than a light breeze on Earth. To be effective, wind turbines would need immense blades or ideal locations, and still their output would be modest compared to solar or nuclear. There is a conceptual appeal, though. Wind blows at night and during dust storms when solar is weak, and it doesn't require imported fuel or extreme technology. For now, wind remains a minor contingency. Perhaps one day they will erect a test turbine with extra wide blades on a tall mast to see what it yields. Likewise, geothermal energy is an intriguing idea. Mars still has some warmth in its crust, as evidenced by occasional Marsquakes, but tapping it would mean drilling deep wells and finding hotspots, a project for far future settlers. Still, knowing that other energy sources exist gives the crew hope that as the colony grows, they can diversify further. Power, like air and water, is now well in hand, and it illuminates and animates every aspect of life here. What was once a dark, frozen patch of Martian ground is now dotted with lights. On a clear evening, one can see the glow of the habitat's windows and navigation beacons at the landing pad, shining warmly against the cold, starry backdrop. In a very literal sense, the base has lit up a small corner of the red planet. With dependable energy, the crew can turn their thoughts to the next step, sustaining themselves in a more organic way. The human body needs not just air to breathe and water to drink, but food to eat. And in the long run, crates of pre-packaged meals from Earth won't suffice. The settlers need to grow their own food on Mars, to turn Martian soil and sunlight into edible sustenance, to close the life support loop with green living things. Having secured shelter, water, air, and power, they are ready to bring a little bit of Earth's biosphere to Mars, seeding the first farm on alien soil. If one were to step inside the new greenhouse module of the Mars base, they might momentarily forget they are on an alien world. The scene is a striking contrast to the ochre emptiness outside. Here, rows of vibrant green plants unfurl their leaves under bright lamps. The air is warm and heavy with humidity, carrying the fresh, loamy scent of soil, though technically it's a soil-less hydroponic medium, and the unmistakable aroma of growing life. After surviving on pre-packaged rations for weeks, the crew finds their spirits lifted by this burgeoning garden. There is something profoundly comforting in seeing green on Mars, a colour almost absent in the natural landscape of dust and rocks. It represents not only sustenance but also a psychological sanctuary, a reminder of Earth's fertile fields and forests, brought down to a human scale in their pressurized shelter. Setting up the greenhouse was an endeavour the crew approached with both scientific rigour and a touch of reverence. They know these plants are not just experiments. They are teammates in a sense, silent crew members that will help provide food, recycle air, and even purify water as part of an integrated life support system. The greenhouse structure itself was part of their cargo, essentially an inflatable cylindrical module about the size of a large shipping container, with transparent sections to let in sunlight when available, and an array of internal LED grow lights for supplementation. Once inflated and attached via an airlock tunnel to the main habitat, it was filled with the same breathable air, and heaters were activated to create a temperate climate inside. In a nod to redundancy, the greenhouse can be sealed off in case of emergency, preserving the plants, even if the main habitat has an issue, or vice versa. The crew began by planting a variety of hardy, fast-growing crops known to do well in controlled environments. Tall racks hold tiered hydroponic trays where leafy greens like lettuce, spinach, and kale are already sprouting. In deeper culture beds, small seedlings of dwarf tomatoes and peppers push up, their stems delicate but determined. There are root vegetables too, radishes and carrots in a soil analog medium, a combination of treated Martian regolith and organic compost from Earth to start the microbial processes. Earlier research had shown that many plants can indeed grow in Mars-like soil once perchlorate toxins are washed out and nutrients added. But for now, the crew opts mostly for hydroponics and contained soil to precisely control the conditions. Water from their reserves, rich now with the minerals that had been dissolved from Martian ice, circulates through the hydroponic systems. It's a constant flow, delivering moisture and nutrients to the plant roots that dangle in the air or substrate. With time, they establish a routine to add nutrients, nitrogen compounds, phosphates, potassium, either from Earth-brought fertilizer or eventually from recycled waste. Lighting in the greenhouse is tuned to an optimal spectrum for plant growth, a mix of red and blue LED light that gives the chamber a gentle purplish glow when the white overheads are off. During the day, if the sun is out, they open the shutters of the greenhouse's ceiling to allow natural sunlight to flood in, filtered through radiation-protective glazing. Martian sunlight, though weaker than Earth's, still carries all the wavelengths plants need and has the advantage of being free. But mindful of cosmic rays and UV, the transparent materials of the greenhouse are made of a special polymer that blocks harmful radiation while letting photosynthetically useful light through. Additionally, for safety, the greenhouse is not entirely transparent. It has thick insulating walls that can seal up during dust storms or intense solar events, with the internal LEDs taking over to give the plants their day. As sprouts turn into leafy bushes and vines begin to curl around support trellises, The crew's daily routines now include the gentle labor of farming. Each morning, 1 or 2 astronauts head into the greenhouse to check on the crops. They wear lightweight gloves and hair coverings to keep the environment clean. Human skin flakes or microbes need to be minimized in this delicate ecosystem. They inspect the leaves for any signs of yellowing or disease. They pollinate flowering plants by hand with small brushes. For now, there are no bees to do it for them. And they adjust the nutrient solution mixes according to sensor readouts. Tiny fans hum quietly overhead to circulate the air, preventing any one pocket from becoming too humid or too hot. Also helps mimic a breeze, strengthening the plant stalks as they respond to gentle movement. The temperature here is kept around a balmy 24 degrees Celsius in the daytime and only slightly cooler at night, encouraging rapid growth. It's as if the plants live in eternal spring and early summer, never knowing frost or scorching heat. Under such ideal conditions, they grow fast. The lettuce and herbs will be ready for harvest in just a few weeks, the tomatoes in a couple of months. The crew has already started planning their first fresh meal, a simple salad of leafy greens and perhaps a cherry tomato each, drizzled with a bit of oil and salt from their supplies. It's a small thing, yet the prospect of eating something fresh and alive, grown by their own hands on Mars, fills them with anticipation. The greenhouse is more than a source of food. It is a cornerstone of what engineers call a bioregenerative life support system. In essence, it is a biological machine that complements their mechanical life support. By design, the greenhouse helps recycle vital elements. The carbon dioxide that the crew exhales is drawn into the greenhouse, where the plants greedily absorb it for photosynthesis, and in return, the plants release oxygen, effectively replenishing the habitat's air supply. The crew's wastewater can be fed to the plants, and the plants transpire moisture that helps humidify the habitat or condenses to be collected. A natural distillery. Nutrients from composted food scraps or other organic waste can be used to fertilize the crops. In this way, plants and humans form a closed loop of inputs and outputs, each benefiting the other in a dance of sustainability. With enough plant growth, the colony could drastically reduce its reliance on mechanical oxygen generators. In fact, the long-term goal is ambitious. Previous studies and prototypes, like the Mars Lunar Greenhouse Project, aim to have a set of greenhouse units provide 100% of the breathable air and about half of the food needs for a crew on an ongoing basis. The crew's current greenhouse is a step toward that vision. It may not yet cover everything. The harvests will supplement, but not entirely replace their stored rations for now. But it is an invaluable proof of concept and a platform to expand upon. Along with recycling air, the greenhouse is also closing the water loop further. Plants transpire water vapor through their leaves as they grow. In the humid greenhouse air, some of that moisture condenses on the cooler walls, or on dedicated condensers at night. The collected water is funneled back into the hydroponic reservoir, effectively creating a rain cycle within the module. Additionally, the crew has started integrating their grey water, like water from washing or humidity condensers, into the plant watering system. Filtered and processed to remove soaps or oils, this water can often be cleaned to a point where plant roots can thrive in it, extracting the last bit of usability. In doing so, the plants purify the water further as well. The multi-tiered approach, mechanical filters, followed by biological uptake, means that by the time water is cycled back to the crew for drinking, it has been through nature's own purifying process in addition to machines. Certain plants, like reed grasses or special strains of algae, are used in a side bioreactor to absorb waste nutrients and neutralize some toxins, functioning as a living water treatment facility. The crew indeed brought a small algae bioreactor that currently bubbles quietly in one corner of the greenhouse. The algae inside feed on a trickle of grey water and on carbon dioxide. In return, they produce oxygen and additional biomass. Eventually, that algae biomass might be harvested as a nutritional supplement or used as fertilizer for the crops. In this way, every output of one system becomes input for another. The settlers are orchestrating a miniature Earth in their habitat, where plants, humans, and machines form a circle of life-sustaining exchanges. Food production, of course, is a primary aim of the greenhouse. Beyond salads, the crew has ambitions to grow calorie-rich foods like beans and potatoes in the future. They have some dwarf bean plants already climbing slender poles in one corner of the greenhouse. Beans have the added benefit of enriching the growing medium with nitrogen via their root bacteria, which helps other plants too. They also have a few potato plants started in an experimental plot using Martian regolith mixed with treated organic matter. This is partly inspired by historical experiments, and yes, a bit by a famous fictional astronaut botanist. But here it's real, and the crew carefully monitors soil pH, salinity, and microbial activity in that test plot. They've introduced Earth soil bacteria to help create a more hospitable environment for the tubers, essentially trying to cultivate living soil out of Martian dirt. If successful, potatoes could provide a hearty, starchy component to their diet in a few months' time, delivering more bulk calories than leafy greens can. There's also the consideration of protein. The crew cannot live on vegetables alone. They need protein sources for muscle maintenance and overall health. For now, much of that comes from stocks of dehydrated meat and plant protein, like soy or pea protein they brought from Earth. But they are looking to the greenhouse to eventually assist here as well. One approach is to grow high-protein plants, for instance, peas or lentils. They have a row of dwarf pea plants nestled in one tray, their tendrils just starting to reach for support stakes. Another approach is to utilize the algae reactor. Certain algae like spirulina are incredibly protein-rich and can be harvested and dried into a powder to sprinkle into meals. The crew is already testing small amounts of spirulina from their bioreactor. It's a vivid green paste that can be mixed into sauces or baked into crackers, boosting their nutritional profile. It might not be the most appetizing on its own, but in a survival situation, it's like growing fish or livestock feed, just in a tank. As the days pass, the psychological benefits of the greenhouse become increasingly evident. Crew members often volunteer for greenhouse duty, even when it's not their assigned shift, simply for the pleasure of spending time among the plants. In the harsh mechanical environment of a space habitat, the greenhouse is an oasis of natural texture and colour. The crew finds that tending to living things brings a calming routine to their lives. Pruning leaves, training vines around supports, planting seeds in little nursery trays. These actions provide a sense of normalcy and purpose that resonates with basic human instincts. At least once a day, one of them comes in just to sit for a few minutes, to breathe deeply and enjoy the extra oxygen, to feel the moisture on their skin, and to watch the gentle sway of leaves under the fans. They sometimes swear the air even tastes a bit fresher in here, sweet with the scent of chlorophyll. And at night, in the habitat, when all is quiet and personal time arrives, some have taken to reading or listening to music in the greenhouse under the soft glow of grow lights as a form of relaxation. The first harvest day is a milestone. A crop of radishes has swollen to maturity and is ready to pull. The crew gathers in the greenhouse, each donning a big grin. Carefully, they loosen the medium around the crimson orbs and tug them out. Clusters of bright red radishes with white root tails emerge, crisp and peppery. They wash them with some of the purified water and then slice a few for everyone to taste. The flavor is sharp, earthy, absolutely delicious for these explorers who have had nothing but stored foods for so long. Never has a radish tasted so good, some of them joke. It's the taste of life on Mars. They also harvest a basket of tender lettuce leaves. That evening, around their small galley table in the habitat, they assemble a simple salad. There are no fancy dressings, no cucumbers or carrots yet, just lettuce and radish. Yet it might as well be a feast. Each crunch is celebrated. In this act of eating what they have grown, they feel a profound connection to their new world. Mars is no longer just a place they are visiting. It is providing for them, through their own hard work and ingenuity. The planet has been, in a tiny way, domesticated. The garden that would barely be a footnote on an Earth farm is, on Mars, the beginning of a whole new ecological system. The success of the greenhouse bolsters the crew's confidence and sense of independence. They know they still rely on supplies from Earth in many ways, but each leafy green and radish is a step toward reducing that reliance. It's empowering to literally hold the fruits and veggies of their labor. And looking ahead, they plan expansions. More modules perhaps, larger grow volumes, maybe even small fruit trees or berry bushes in later phases. Visions of a Martian orchard or fields of wheat in pressurized domes dance in their heads. It sounds fanciful now, but so did growing even this much food not long ago. Crucially, the integration of plants also provides a safety buffer in emergencies. If the life support systems falter, the greenhouse can act as a temporary refuge with fresh oxygen. If stores of food run low or a resupply mission is delayed, the plants can stretch their rations with vitamins and some calories. In a worst-case scenario, seeds themselves are lifelines. They have crates of seeds for multiple plant varieties stored carefully, each one a packet of resilience, a tool to restart growth if needed, or to try new crops as conditions allow. With plants flourishing and providing nourishment, the Mars outpost starts to feel not just like a campsite or survival bunker, but a living settlement. The static mechanical hum of the life support is now accompanied by the quiet rustle of leaves and the gentle trickling of water in hydroponic tubes. Life, biological life, has joined the equation of sustaining humans on Mars, and life tends to multiply. The colonists imagine that years in the future, their greenhouse might evolve into a larger farming complex, complete with chickens or fish in aquaponic setups, insects to pollinate and even to eat, crunchy cricket snacks someday perhaps, and a diversity of crops that could make them effectively agriculturally self-sufficient. It's not an easy road, but the path has been opened. In the meantime, there is work to do in maintaining this delicate Eden. As robust as plants are, the Martian greenhouse is a controlled ecosystem that requires careful management. The crew rotates the crops to even out light exposure, prunes any fungal growth. When a bit of powdery mildew tried to start on a cucumber seedling, they removed it promptly, and calibrates the watering and nutrient systems to keep conditions optimal. They also start a composting experiment, a bin where inedible plant matter, like radish tops and wilted outer leaves, and other biodegradable waste are combined with a bit of earth soil and some worms they've brought along in a small culture. Yes, they brought worms to Mars. These little wrigglers, if they survive and multiply, can help break down organic waste into rich compost. The first batch of Martian compost, when ready, will be a treasure trove of fertilizer for future plantings, containing all the micronutrients and beneficial microbes to keep the soil healthy. It's another loop closed, waste becoming nourishment again. The greenhouse and its bioregenerative systems symbolize something even larger, the possibility that humans can truly live off the land, even on Mars. The settlers have proven that a combination of technology and biology, of steel and soil, can sustain human life far from its cradle. Each system in the colony, water, air, food, energy, is coming together as an interconnected web, a prototype of future Martian cities where green parks might flourish under domes and fields of crops might sway in artificial breezes. It's a vision that keeps them motivated each day. Now, having tackled the fundamentals of survival, the crew knows that sustaining and growing their presence will require extending their capabilities further. They will need to build more, repair what breaks, and innovate new solutions on the fly. They will need machines to assist in tasks that humans alone cannot do efficiently in this environment, and they will need the ability to make and fix those machines as well. Essentially, after tending to the garden of life, it's time to ensure the tools of civilization are firmly in hand. This means diving into robotics, manufacturing, and the intricate dance of human and machine cooperation. The colony is stable for now, but to truly thrive, it must be able to expand and maintain itself with as little dependency on Earth as possible. Ahead lies the story of the mechanical companions that toil alongside the humans, the robots, the fabricators, the spare parts, and the know-how that will build a new world. As one chapter of establishing life closes, another of building and expansion begins, seamlessly continuing the saga under the same alien sky. In the quiet pre-dawn hours on Mars, while the crew sleeps inside their sanctuary, a different kind of activity continues unabated outside. A quartet of autonomous robots trundles around the outpost, performing their programmed duties with tireless precision. These machines, which the crew fondly nicknames Digger, Printer, Sparky, and Watchdog, are as much a part of the base's operations as any human. In fact, they often work when the humans cannot, such as during the long stretches of night or when conditions outside are especially inhospitable. Their presence allows the outpost to be productive around the clock, an essential force multiplier for a small crew on a big planet. Digger is a rover outfitted with excavation tools. In the faint light of Mars's 2 moons, it methodically scoops and moves soil, continuing to build up radiation berms around new structures and clearing trenches for cables. Its latest task has been to dig a shallow trench between the main habitat and the newly erected communications antenna, so that a durable cable can be buried and shielded from both radiation and the wear of temperature swings. Watching Digger work is like watching a diligent mole or an ant. It's single-minded, making repeated trips back and forth, carrying loads of regolith in its bucket. Long after humans would tire, Digger keeps going until its battery runs low, at which point it navigates itself back to the charging station, aligns with a dock, and tops up on power from the grid. Come morning, it will resume exactly where it left off. This kind of automation ensures that many of the heavy, laborious jobs are taken off the crew's shoulders. They can focus on planning and supervising rather than pure manual labor in a suit, which is exhausting and constrained by limited oxygen. Meanwhile, Printer, another robotic workhorse, has not been idle either. This is the large 3D printing rover that helped build their habitat's shield walls. With that major construction completed, Printer has moved to the workshop area and been retooled slightly for fabrication duties. By swapping out its large extrusion nozzle for a finer one and adjusting its software, the crew has effectively turned Printer into a mobile manufacturing unit for spare parts and tools. Inside the pressurized workshop tent, which is kept at a lower pressure and often not entered by humans without suits to conserve resources, Printer now works on a queue of tasks the crew assigns. At the moment, it is fabricating a replacement part for the greenhouse's water circulation pump, a small impeller that has shown signs of wear. The design for this impeller was already in their digital library, sent from Earth, and the engineers on the team have tweaked it slightly to better suit Martian gravity and the available materials. Printer uses a combination of materials for such jobs. For plastic parts, it has spools of high-grade polymer that can be melted and deposited layer by layer. For metal parts, it switches to a laser sintering print head, using a mix of powdered aluminum and Martian regolith as feedstock, sintering them into a solid piece. The regolith-derived ceramic pieces lack the tensile strength of, say, forged steel from Earth, but for many applications they are perfectly sufficient. Over time, this machine will produce brackets, gears, casings, and other components, essentially giving the colony a basic on-demand factory. The crew occasionally watches Printer's progress via camera feed inside the hab. It's mesmerizing to see an object appear seemingly out of nothing. A thin cross-section on one pass, then a bit thicker on the next, and gradually a recognizable shape emerges, drawn in metal or plastic. When the impeller is done, Printer lets it cool, then one of the crew retrieves and tests it. If all is well, they swap it into the pump, and the greenhouse's water system gains a fresh lease on life. The old impeller, rather than being thrown away, goes into a bin to be melted down later as raw material for something else. Efficiency is key. Nothing useful is discarded on Mars if it can be reused or remade. Sparky is the affectionate name given to a multi-jointed robotic arm installed on a movable base, essentially a mechanic on wheels. Sparky's domain is maintenance and assembly. In the wee hours, Sparky might be found rolling along the perimeter of the habitat, its camera eyes glinting in the starlight as it performs a routine inspection. Its sensitive instruments check for any signs of leaks or structural stresses on the habitat exterior. It can detect the subtle hiss of air escaping or the fine line of a crack on a solar panel mount. If something is amiss, Sparky has tools to address minor issues. Sealant dispensers, a gripping hand to tighten bolts, even a welding torch attachment to mend small cracks in metal. For example, on one occasion, a micrometeorite, a tiny high-velocity space rock, punctured an outer layer of one of the storage tanks. The crew was alerted by sensors, but it was Sparky that quickly trundled over and patched the hole with sealant and a laser weld, sealing the leak before it became critical. This quick response would have been difficult for a human to manage in time, especially if it happened during a crew rest period, or when the astronauts were busy with other emergencies. Exactly the scenario mission engineers envisioned when they equipped the base with autonomous repair bots. Sparky essentially acts as the colony's tireless maintenance worker, performing regular tasks that would otherwise consume valuable astronaut time. It replaces filters in the life support system by maneuvering through a back maintenance airlock, swapping cartridges with its adept arm according to schedule. It cleans dust off sensor lenses and lubricates joints on other robots. The idea, as advocated by planners on Earth, is to let automation handle as much of the mundane upkeep as possible. That frees the humans to focus on higher-level work, exploration, science, planning the expansion of the base. It also adds a safety layer, enabling rapid response to emergencies as described. In effect, the robots extend the crew's presence. They can be out there doing 3 or 4 things at once in different locations, like extensions of the astronaut's own hands and eyes. Then there is Watchdog. Watchdog isn't a builder per se, it's a guardian. It's an autonomous drone, a small quadcopter similar to the tiny Ingenuity helicopter that scouted Mars alongside Perseverance, but a more advanced model with longer range and improved autonomy. In the thin Martian air, rotors have to spin furiously to generate lift, but Watchdog is lightweight and its blades are broad. By day, it recharges via a small solar panel or at a power station. By night, or whenever the crew wants an aerial view, Watchdog lifts off to patrol. It provides an eye in the sky, mapping the terrain around the base, looking out for dust devils, and checking the integrity of far-flung assets, like their communications relay on a nearby hill. It can also scout new ground for future expansion or resources, identifying, for example, the best path to a nearby cliff, where interesting mineral veins were spotted from orbit. Watchdog's cameras feed back to a console in the habitat, where the crew can watch live or recorded flights. Seeing their home from 100 meters up gives the astronauts a perspective of progress. What started as a single lander and a tiny hab is now a complex of connected modules, solar fields, and excavation lines, the beginnings of a settlement visibly etched on the planet's surface. The collaborative dynamic between humans and robots at the base is one of quiet teamwork. The crew has learned to trust their mechanical partners for many tasks, but they remain vigilant managers. The robots are given a degree of autonomy. They carry out scheduled routines and can handle minor obstacles, like driving around a rock or retrying a task if it fails the first time. However, the human crew oversees critical operations and can take manual control via remote interface if needed. Each morning after breakfast, the team holds a planning meeting where they also review what the robots accomplished overnight. Did Printer finish that part? Did Digger complete the trench? Did Sparky report any anomalies during its inspection round? Usually, all is well and progress was made. Occasionally, they find a hiccup, like Printer pausing because a material feed jammed, or Digger halting when it encountered a rock too large to move. They adjust their plans accordingly. Perhaps someone must go clear that rock, or reload Printer's feedstock. It's all part of the new normal on Mars, where one's co-workers include not just other astronauts, but metallic assistants on wheels and legs. As their habitat and outpost grow more complex, the presence of these machines also adds a safety layer for exploration. Soon, the crew plans to make longer forays away from base, to venture into that lava tube properly, to survey the crater interior, to collect geological samples from farther afield. When they do, they can leave some robots in charge at home. Sparky, or its twin, can handle small issues that arise while they're away, swapping a filter or tightening a loose fitting. Watchdog can keep an aerial eye on the base from above. If anything critical happens, an alert will reach the crew via their communication link, and they could hurry back. But knowing the base isn't completely unattended is a relief. Conversely, when they go exploring, they'll take robots with them, perhaps a teleoperated scout rover to drive ahead and assess terrain, or a drone to map as they traverse. The integration of robotic systems essentially extends their senses and capabilities, making the humans far more effective in both settling and exploring. In one scenario, a crew member envisions they might someday send a convoy of robots out to begin constructing a second habitat module site a few kilometers away, perhaps near a large deposit of ice or a particularly interesting scientific zone. Those robots could lay groundwork so that when humans arrive, much of the heavy lifting is already done. This is exactly how their first base was partially prepared. Certain cargo and robotic units landed ahead of them and got to work building the landing pad and shielding. It's a strategy they plan to keep leveraging as they expand. One can imagine, in the future, an entire robotic construction crew building out new greenhouses, digging foundations for new living quarters, even assembling additional nuclear power units, all with minimal direct human labor. As sophisticated as these machines are, they are not infallible. The crew remains prepared for a robot to break down or a program to glitch. They treat the robots almost like fellow crew members. They must be kept healthy through maintenance and occasional rest for software updates. For example, when Sparky's arm joints began to show wear from fine dust abrasion, the crew brought it into the workshop for a full tune-up, cleaning out dust, replacing some joint seals with spares, lubricating moving parts. Dust is a relentless foe to anything mechanical on Mars, so the engineers have designed the robots with sealed components or dust-wiping features, and they schedule regular refurbishments. After so many hours of operation, a robot is brought in for preventative maintenance, much like servicing a vehicle after a certain mileage. This practice prevents many failures from catching them off guard. A broken robot at a critical time could be disastrous. Imagine if printer failed just when a vital part was needed, or if digger's power unit died in the middle of digging a protective trench. So they aim to anticipate and avoid such events. In the evenings, sometimes the crew shares a lighter moment about their mechanical colleagues. They might chuckle about how Digger, during a calibration routine, carved a pattern in the soil that looks like abstract art, or how Watchdog once followed a dust devil, like a curious pet chasing its tail. These anthropomorphic asides remind them that, despite the seriousness of their mission, they are allowed to find whimsy in their day-to-day. And indeed, the robot's movements can sometimes seem almost lifelike, especially when you spend so long with them. It's no wonder that rover teams back on Earth gave their robots personalities. Here on Mars, with such a small human company, the astronauts half-jokingly treat the robots as part of the family. The synergy of humans and robots forging a foothold on Mars is a testament to planning and adaptability. It illustrates a profound change. Humanity isn't facing the Martian frontier alone, with just muscle and willpower. We've brought along helpers, extensions of ourselves built from metal and silicon, to share the burden. This teamwork has allowed the base to reach a level of stability and functionality that might otherwise have taken a much larger human crew to achieve. With construction and maintenance largely handled and food production underway, the colonists have more freedom to think about the next steps: expansion, exploration, and ultimately the transition from a tiny outpost to a true colony. Already, around the initial landing zone, things are evolving. What began as one habitat is now a cluster of structures, some for living, some for working, some for storage, connected by cables, pipes, and pathways. The outlines of streets, or at least well-trodden routes, are emerging in the dust between modules. To carry this endeavour forward, thought must be given to organising and connecting these growing parts of the colony. This means planning out tunnels or covered walkways for safe passage, adding new habitat blocks as their population grows, and developing ways to travel farther from base when needed. The dawn of a Martian village is at hand, and with it comes the task of building infrastructure akin to roads and thoroughfares, albeit ones that might run under protective layers or within pressurized tubes. The team readies themselves for this next phase, making a true community layout on Mars, where not just survival, but daily life and movement are accounted for. Their machines stand ready to aid in digging those pathways and erecting those modules. In the distance, the stars shine over the silent desert, as if awaiting the lights of a little city to join them in the Martian night. The adventure continues, as this small band of pioneers sets the stage for a future city under the stars on Mars, one careful step and one inspired dream at a time.